Hello, everyone, and welcome to the 2020 version of the Wolfram Technology Conference. I am pleased and honored to introduce Stephen Wolfram.
Hi there. Okay. Well, welcome to the 31st year of our annual technology conference. And the first time it's been virtual. It's a shame to not be able to see people in person, but it's good that a bunch of additional people are able to attend because it is virtual. So it's been it's been a little over 32 years now since we launched Mathematica, and it's hard to believe, but I think we have even more to discuss today than we ever have done any previous year. It's kind of like, after 32 years, haven't we finished everything yet? No. Actually, the more we build, the further we can see, the further we can go, the faster we can go. There are a lot of long-term projects that we've been working on, some of which are just now coming to fruition, and I'll be excited to tell you about some of those things. And there are some projects that are shorter term that have been started even in the past year or so that are coming to fruition that I'll also be able to tell you about. So I'm going to talk about several different kinds of things here. Yes, I'm going to show you lots of new technology that's coming, particularly in version 12.2. Which should come out in the next month or so. But I also want to talk about kind of the big picture of what we're doing and what we're trying to do, and about the very important role that you and our community can and should play in what we're trying to do. Well, this time last year, we had just released version 12.0. Let me arrange myself here. Oops. And I want to. Okay, we had just released version 12.2, 12.0. And let me make that bigger. We released this actually in April of last year. We were about halfway through the 12.1 development cycle. 12.1 was released in March 18th of this year. Actually last October, it took me 4 hours to go through the features that were upcoming in 12.1. So I'm going to try and go much faster here today. Let me mention the highlights of 12.1 because what came out in the final 12.1 was a bit bigger than what was in the preview that I showed you. So there were a total of 182 new functions in that 0.1 release, which is a pretty remarkable thing that a 0.1 release ends up with 182 new functions. This is just a list of those new functions. So I wrote about this at length, as I'm wont to do here, you can find all sorts of different things about the different features of 12.1 that I wrote about back in March of this year. So it was a very impressive collection of new functionality. Big effort to get it out right in the middle of an emerging pandemic, just to make things even more exciting. But after 12.1 came out in March of this year, we decided to do something we hadn't done before, which is to have a release that was a pure polishing release. So 3 months later, we brought out version 12.1.1, June 17th. And the main thing about 12.1.1 was that it had 1,000 bugs fixed in it. The oldest one was a documentation bug, actually, from 1993. The oldest code bug was from the year 2000. And here's an image that I made as a, oh gosh, these are all coming out too small. Here's an image that I made as a kind of a tweet image to illustrate our various bugs of different severities that got fixed in that release. Okay. So what happened in the 3 months since June? I should explain that we always have a big pipeline of new stuff coming. There's some projects that have been running for years, others that are quite new. And if you've been watching our live streams, you will have seen a lot of this sausage being made. You will have seen a lot of the designs for the things that are coming in version 12.2 being developed, and beyond 12.2 actually. We've so far done about 400 of these live stream design review meetings. We found it a very productive way to work, not least because we have a terrific group of people who tune into these live streams and give us suggestions and real-time feedback, and that's been really helpful. And in version 12.2, you'll see a bunch of things that was suggested by people on our live streams actually come to fruition and be released as a piece of the product. So we're very happy about that. Well, okay, let me give you kind of a bit of a summary of what's coming in 12.2. There are, at current count, a bit over 100 new functions, all finished in the past 6 months. It's kind of an interesting set of data points. In the 1 year between version 12.0, which had 278 new functions, and version 12.1, there were 182 new functions accumulated. In the 6 months since version 12.1, we've accumulated about 100 new functions that will go into 12.2. So a sign of what feels to me like it's acceleration, and that's what we see in terms of the count of number of functions. Just a recap of some of the things that were new in 12.1, things like the data structure functionality that came out of our compiler project, asymptotics as a way of doing a new level of symbolic analysis, things to do with data set and its formatting and table view, things like cross-hatching of graphics, a kind of whole calculus of annotations approach to dealing with annotations in graphs and images and all sorts of other things. Things in sort of functional programming and symbolic programming like splice and operator applied and so on. A lot of stuff to do with geo-computation meets geometry, being able to treat geographic things using our geometrical computation capabilities. Things like external identifier and Wikidata data as ways to reference canonical external kinds of entities. Things about molecular structure OCR. In 12.0, you might know that we introduced a lot of capabilities around molecular and chemical computation. Also in 12.1, external storage capabilities, and also sort of first classing our Paclet system for releasing, for distributing kind of additional functionality for the system. Okay, so what's there in 12.2? So what I'm going to do, I consider this a bit of a spoiler for what's coming later, but I want to give you some indication of some things, and I'll talk about a bunch of other kinds of topics. So in 12.1, we started on video, putting video as a first class kind of thing in Wolfram Language. There's a lot more of that in 12.2, although it's very strong there, although still not finished there. In geocomputation, we've got things like vector maps. We've got a big effort in spatial statistics. We've got more in synthetic geometry, drawing Euclid figures, drawing molecules. We've got a new effort in biosequences for DNA and proteins and making all of that computable. We've got a bunch more hardcore math of things like function properties, more asymptotics, a bunch of new algorithms we've invented, more on convex optimization. We've got a big new PDE, partial differential equation modeling framework. Also things in machine learning, ability to make custom layers and finer control of the kinds of things that we can do, and compilation and so on. Also actually deployment to external devices and such like. We've got another big area is remote batch cloud jobs, and also some cool and perhaps unexpected user interface capabilities. That's kind of the coming attractions of version 12.2. All right, I want to talk about that in much more detail later, but first let's talk about some other things. Well, of course there's been a pandemic, and we've been kind of trying to do our part. Let me see, what's this? Is this? Oh, no, that's not what I wanted. Okay, we've been trying to kind of do our part to support the world in this unusual event. And since we're a data company, from the very beginning, we were curating and deploying in computable form on the web data about the pandemic. We've been doing that every day since the pandemic started, and I think people have been finding that very useful. We have a variety of different kinds of data. We've also been doing lots of computational essays by people in our community and ourselves about what one can do with that data, and a variety of other things here that are directly kind of providing sort of computable support for pandemic related analysis. So I must say, I started off really trying to study the epidemiology of the pandemic and decided that it's a lot harder than one thinks, and there's a lot of data one doesn't have, and a lot of conclusions one can't make, and much that I think is still mysterious about what's going on, but let's not talk about the science of that here right now. But another very practical thing that we did was simply providing resources for universities and so on to make our products more readily available in these kind of virtual times. That's been particularly leveraging our cloud technology and in terms of providing access to Mathematica Online, and that's been a very successful program. Another thing that we've been doing just recently for this school year is providing some homeschooled courses, which are just about to start up for students who are not able to be in the schools they would usually be in. We've also, another quite different kind of thing, people can't do lab experiments as readily in these times, and our system modeler product line has had found lots of use in being able to do virtual experiments that can be done without being physically there. So there's also at the research level of studying the pandemic, lots of use of our technology, and I'm looking for, there we go. Here's actually a word cloud of papers this year that have cited our technology, and you'll see all kinds of different topics covered here. And there's a cluster somewhere here for epidemiology and COVID and so on. I'm not sure I can find that cluster and all of the, oh, there we go. There's a COVID-19 cluster, and there'll be other ones here for various kinds of epidemiology and so on. But it's been nice to see our technology used not only for epidemiology, but also for things like fluid flow studies and so on related to the pandemic. You know, in all the bad things that have happened with this pandemic, there are also some things that it's nice got pushed to happen. I've been doing myself a number of kind of public service kinds of things. One thing I started pretty early in the pandemic was a weekly kind of science and technology Q&A for kids and others, which we've been live streaming, and I've at least been having a lot of fun with it. We've have a bunch of sort of podcast episodes here from it. And I think it's helped make me a bit of a better explainer of all kinds of things and all kinds of strange questions that come in. So that's been something that that has been a productive thing that's come out of this. Of course, this is a good time to have a geo-distributed company. We have such nice offices in places like Illinois and in the UK and so on. It's a shame that they have been so abandoned, but we have been a geo-distributed company for 30 years now. And that's been something which has meant that we've been able to continue to be productive through these times. I myself have been a remote CEO now for 29 years, and people used to say, what a crazy thing to do. But in these times, it doesn't look quite so crazy. And they were like, you were ready for this all along. Okay, well, so nobody expected this pandemic. And but another thing that was very unexpected for me personally that happened in this past year our physics project. That was another very surprising thing in my life, so to speak. As some of you may know, well, a year ago at our technology conference last year, I said I was going to work on this, and indeed I did. And it turned out better than I could ever possibly have imagined. It's exciting both for the physics of what it's brought and for a bunch of applications that it's provided, and also for a bunch of meta lessons that I have learnt from the very doing of this project and the fact that it was possible to do it. Well, so by way of backstory, as many of you may know, I used to do physics when I was a kid, but I've been sort of out of the business professionally for about 40 years now. And for those who may be here who knew me back in the day, yes, I'm sort of back again now. I mean, I've been, in those intervening years, I've been sort of alternating between basic science and technology, about 5 cycles, I think, so far. But back in the day, 40 years ago, I was very interested in fundamental physics and worked a bunch on that, and then kind of got involved in what I saw as being something, in a sense, more fundamental than that, and going beyond the kind of the sort of mathematical models and so on that we've developed and had been developed in fundamental physics, and trying to see what are the sort of most fundamental models that we can make of things and so on. And that led me into studying computation and programs and so on as sort of a more fundamental substrate for the ways that one can build up models of things. And sort of from that effort spun off the things that in complex systems research and so on, even if that particular field didn't work out entirely as I might have liked it to, it was a nice thing to kind of spin off from those early studies. But the real sort of question that I was interested in at that time was, okay, if we're going to take programs and computation as sort of the foundation for how things work, what does the typical program actually do? And for those who are not aware of this, let me just bring up a few kinds of things here. So if what I got interested in was some sort of very simplest possible kinds of programs. So this is a cellular automaton, just a line of black and white cells. And here's a rule that says what the next color of a cell will be after it has a particular arrangement of cells on the previous step. So if we run that rule for a few steps, we'll get this kind of pattern here. We're just starting off with one black cell at the top there. And it's a very simple rule, and we get very simple behavior. Do the same thing here, and we can run that again. And again, we'll get very simple behavior. So the question that I first sort of asked about in the early 1980s was, okay, so these simple programs produce very simple behavior, but is that true of all simple programs? If I just look at all possible simple programs of this type, for example, what kind of behavior will they all produce? And so these days it's very easy to do that computer experiment. Here's the result. And we see that each one of these pictures corresponds to a different program, a different rule. And we see that many of them produce very simple behavior. Maybe some of them produce these nested fractal patterns and so on. But kind of pointing this sort of telescope into this computational universe of possible programs, the most remarkable thing that I saw back in 1984 or so, is actually, I saw it earlier than that, but didn't realize what I'd seen until about 1984, was this thing that I call Rule 30. And if we go here, go down here, and let's just look at Rule 30. Here's the rule that it has, and let's just run that rule. Let's say we run it for 400 steps here, just starting off from that one black cell at the top. And I should have typed 30 there. Then this is the behavior we get. And oops, what did I just do? So single black cell at the top, very simple rule, yet the behavior we get is far from simple. In fact, for example, if we look at the center column of cells down here, for all practical purposes, it seems completely random. So this is really, for me, was a very remarkable thing, a very kind of intuition-breaking kind of discovery, kind of my all-time favorite science discovery, that in this computational universe of possible programs, even a program as simple as this can sort of effortlessly produce great complexity in its behavior. And I think that's sort of a fundamental result and a fundamental fact about the way the computational universe and abstract programs work. And it's something that over the years since that time, I've done a lot to try to understand the consequences of that kind of that scientific discovery. And over time, that sort of gave me a whole new way to think about all sorts of kinds of science. In fact, eventually it led to this big book that I wrote called A New Kind of Science, which tried to apply that kind of what I discovered from sort of exploring the computational universe of possible programs to all sorts of different kinds of systems in nature, and to modeling all sorts of kinds of things, from biological growth to fluid flow to lots of other kinds of things like that. And by the way, it's been a really nice thing to see, because historically, there'd been for about 300 years, there was kind of this dominant idea that if you wanted to make models of things, mathematical equations were the place to go. And I would say in the last probably 20 years or so, there's been a real transition towards when a new model is going to be made of something, the vast likelihood is that it will be a model made in terms of programs, not in terms of equations. And that's a big deal, that after 300 years, we've managed to get in only 20 years, a real transition to new models being made primarily in terms of programs. And that's, for me, an exciting thing. It's also, by the way, when we look at this sort of computational universe of possible programs, it's also a great place to mine technology from, to find these programs that do interesting and useful things. And just like we find interesting and useful materials in the physical world, we can kind of mine these programs to use them as algorithms for things that we try to do. But when I wrote New Kind of Science, one of the use cases for the kind of methodology that I was developing of exploring the computational universe and simple programs in it, one of the use cases was, can this be applied to fundamental physics, to a theory of our whole physical universe? And I wrote about 100 pages about that in the NKS book, and I figured out quite a bit about how that might work, and I was pretty pleased with some of the results I got. But I only viewed it as kind of a use case for my main methodology, and didn't really take it as far as I could have done at that time. Unfortunately, even though in a sense, the market found the idea of modeling with simple programs really interesting for many areas of science and technology and engineering and so on, in fundamental physics, there was very much of we've been doing mathematical equations now for a few hundred years. They're working just fine for us. Thank you very much. We don't need anything new. And so the result of that was that I basically didn't end up working on developing the fundamental physics directions of New Kind of Science. Instead, I worked on little things like Wolfram Alpha and then Wolfram Language and so on, and building our whole sort of computational language vision. And so I was very happy to do that. But then about a year and a half ago, a couple of years ago, I made a little bit of a minor methodological breakthrough in thinking about sort of fundamental physics. And a couple of young physicists told me, you just can't leave this stuff undone. You just have to go and push forward and try and see whether it really works to think about fundamental physics in these kinds of terms. And so we did, and it's worked out just great. Well, I thought it would be a lot harder than it actually turned out to be. I mean, I thought that we would sort of we might be able to get to the first kind of 10 to the minus 100 seconds in the evolution of the universe, and then we'd be fighting with this phenomenon of computational irreducibility. We kind of can't foresee what the consequences of our computations will be much faster than just running them. We'd be fighting with computational irreducibility, and we wouldn't be able to see much past that. But the big surprise is that, in fact, we have been able to go a lot further than that. In fact, we've been able to see that from these very simple underlying ideas and very simple underlying framework, we're able to reproduce, for example, the two great pillars of 20th century physics, general relativity and quantum field theory. And that's a really exciting thing. And what we found is that from a model that is just outrageously simple, we're able to go and kind of progressively check off more and more aspects of what we know in physics. And it's going just spectacularly well. I mean, I'll just give a very rough walkthrough of what's what goes on here, and I'm going to talk about this some more on Thursday evening for people who are interested. Basically, one of the key ideas is to think sort of underneath space and time. What are they made of, so to speak? And usually when we think about space, for example, we don't think what it's made of. We just think it's some manifold and we can place a point wherever we want. That's been kind of the idea the last couple of thousand years. The idea that we start from is something sort of more computational. Imagine that there are just atoms of space, just points. And imagine that we have this kind of structure that represents space that is just a bunch of these points, and all we know is how these points are joined to each other. They're joined like in a network, or in fact, in general, in a hypergraph. And so then what we say is that's sort of the structure of space. Now, the way that time works is that at every moment, we're looking around in this hypergraph and we're saying there's some simple rule that we might use that can rewrite a piece of the hypergraph to some other form. And we just apply that over and over again. And just like in the case of something like Rule 30, we can go from a very simple initial condition, very simple rule, and we build up these very complicated structures. These structures end up on a very large scale having properties that can be very much like the space that we're used to seeing. It's kind of like what happens in fluid dynamics when you start off from that sort of microscopic molecular dynamics of a bunch of molecules bouncing around, and then on a large scale, you see continuum fluid mechanics. In our case, instead of getting continuum fluid mechanics from these atoms of space kind of interacting, what we get is Einstein's equations for the structure of space-time. So that's already quite exciting. Another thing that happens is that as we look at kind of this rewriting of hypergraphs in terms of these simple rules, one of the things that's sort of inevitable is that there are many possible ways that that rewriting could happen. And that means that instead of thinking about a sort of single history for the universe, we're thinking about this whole kind of multi-way graph of possible histories for the universe. And it then turns out that this multi-way system actually reproduces the things we expect in quantum mechanics. And in fact, right now we're sort of close to having some kind of formal proof of the exact equivalence of our multi-way systems to things like categorical quantum mechanics and so on, which kind of nails the case shut, so to speak, in terms of the equivalence of our models, in that case with quantum mechanics. We can already see many kinds of things that that correspond, and we can, and so on. One of the things that's really nice is, for example, we end up in this kind of multi-way graph. We end up having something which is kind of the equivalent, when we kind of slice space-time in time slices, we get space. When we slice the multi-way graph in time slices, we get something that isn't space, but it's a bit like space. It's a thing we call branchial space. It's a space of branches. It's a sort of a map of quantum entanglements between different quantum states. And one of the things that I think is really cool is that the kind of the behavior of paths, behavior of geodesics in physical space, and the Einstein equations that govern how physical space work, what the precise analog of those equations in branchial space is none other than the Feynman path integral for quantum field theory. So in a sense, if one was wondering for these two pillars of 20th century physics, which have had a hard time sort of being knitted together, what we've discovered is that actually in some sense they are the same theory, except one operates in physical space, the other operates in branchial space. So a lot of things that a lot of things coming out of this, a lot of really, really interesting physics and mathematics. One of the things that's been particularly interesting to me is that a lot of approaches to mathematical physics of the more abstract, particularly the more abstract ones, they seem to all be kind of connected to our approach to physics. It's almost as if we have this kind of Rosetta Stone for all of these kinds of very abstract mathematical physics. A little bit like what happened back in the 1930s when Turing machines were invented. There'd been these other approaches like combinators and lambda calculus and general recursive functions and so on to the idea of computation. But once one had sort of the concreteness of Turing machines, one could kind of see how all these pieces fit together. And I think that's what's happening with our model of physics and kind of approaches to mathematical physics. Well, it's there is one kind of amazing, if embarrassing, point about this whole model of physics. You can say, what's the sort of fundamental data structure of the universe according to this model of physics? Well, ultimately it's basically a symbolic expression. And that's sort of embarrassing because I've been thinking about symbolic expressions for 40 years now, and they're the foundation for Wolfram Language. They're the foundation of SMP, the precursor to that. And there's something I've been thinking about for a very long time. And for various reasons, I never really imagined that that one could be thinking about a symbolic expression with 10 to the 400 elements that would represent our universe. I was always hung up on the idea that symbolic expressions should be built to mean something rather than be purely structural kinds of things. But now what we realize is that that same idea and many of the issues that come up there are the things that we can use to build kind of this fundamental data structure for physics. Well, and it turns out just as cellular automata are sort of minimal idealizations of parallel computation, so these new models that we have are kind of minimal idealizations of computation where things happen without space, without time, asynchronously, and with arbitrary kind of connectivity and structure. And so it turns out that not only are these things interesting models for physics, they're also interesting models for lots of other kinds of things. And there are many other applications that are emerging. One of the ones that I've been looking at quite a lot is a bulk theory of metamathematics, a kind of theory of how mathematics grows and how the network of all possible theorems of mathematics is laid out in kind of metamathematical space. There's also the possibility for a new kind of approach to theories of biological evolution. There's also a new approach to thinking about distributed blockchain that's coming out of this. And in general, one of the things that's sort of really remarkable is that a lot of the issues about physics have direct analogs in distributed computing. Things like the uncertainty principle in physics, direct analog in the way that things work in the non-commuting of operations in distributed computing and so on. And a lot that can be learnt from 20th century physics, for example, that can now be applied to distributed computing and vice versa. Well, another thing to say is that this project of ours really wouldn't have been even conceivably possible without Wolfram Language. I mean, that's what basically made this project possible. We're making all the code for the project directly available. There it is. Those are all function repository functions that you can use to run all these different aspects of our models. We've been treating this as a very open science project. We've been kind of doing the science, both the science itself and the way we've been doing the science is, I think, a different and a sort of take on what's possible. So we've been live streaming everything we've been doing and building hundreds and hundreds of hours of live streamed archives. In fact, I'll show you one thing here. Let's see. Yeah, this is kind of cool. This is actually makes use of our new video capabilities. All of these live stream archives were processed with the new video capabilities in Wolfram Language. We're also making available all of the notebooks that have contributed to this project going all the way back to 1994. And it's really cool for me to be able to take a notebook that I produced in 1994 and just start it up and run it. I mean, that to me is a great sign of longevity and stability of our language, that's possible. And well, okay, so there's lots going on with our physics project. There's a whole group that's forming around it, and we're doing all sorts of study sessions for people who are interested. We collected the kind of the launch documents of for this project in a physical book. Here we go. This is the physical book. There we go. Actual physical book. It actually looks really nice. It's these images produced with Wolfram Language and with our graph capabilities and so on come out really nicely there. But in any case, it's I view our physics project, if nothing else, as a fantastic use case for Wolfram Language and a fantastic sort of endorsement of the computational approach to everything. I mean, it's computation all the way down, and we can really see that now. Well, but in a sense, even the bigger story than sort of how physics works is this whole story about computational language and about describing the world computationally at all levels, not just at the level of fundamental physics. And this is kind of a mission that I've been on for the last 40 years or so, to ask the question, we have this sort of paradigm of computation, what can we do with it? And it's a paradigm that eventually affects everything in our way of thinking about basically everything. So, in a sense, I have a certain point of view now about kind of how the science of this and the philosophy of this fits together. On the one side, we have the computational universe with things like Rule 30 and all of the kinds of models that we have of fundamental physics, where there's this kind of ocean of computational possibility. All of these different systems, even with very simple rules, that do all these very, very complicated things. That's sort of the power of computation, that we can see throughout this computational universe. That's kind of thing number one. Thing number two is what we humans think about, the actual kinds of objects that we discuss, the things that we talk about in our human languages and so on. That's sort of thing number two. And I think one of the big challenges is to make a bridge between those two things, to find a way to sort of connect what we think about with the sort of ocean of computational possibilities that exists. And in a sense, I've spent most of the past 40 years trying to build such a bridge, and that bridge is the computational language that we've created with Wolfram Language. It's a bridge that tries to connect what's sort of computationally possible with the things that we humans think about, and giving us a way to kind of form our thoughts in such a way that they can be connected to this kind of computational capabilities. In a sense, it's kind of, what is the idea of a computational language? It's not like a programming language. A programming language is something which just sort of tells a computer step by step what to do. The idea of a computational language, and Wolfram Language is the only example of such a thing, it's a language which tries to describe everything in the world computationally. It tries to describe whether the thing you're describing is a piece of an algorithm, something abstract, whether it's a physical thing about a movie or a location on the earth or whatever else. All of these things, we're trying to describe them computationally. We're trying to have a way to take those things and have a precise symbolic computational representation of those things. And to do that, we have to build into our language a lot of knowledge about the actual world and a lot of knowledge about computation. And that's what we've been trying to do for all these years in Wolfram Language. And one of the things that we get at the end of this is a language that is not only something that is relevant for explaining something to computers, it's also relevant as a way to focus what we humans are thinking about. So as you kind of think in computational language, you're kind of casting your thoughts into a definite form that has a kind of computational structure. And that's a really important thing to do. In a sense, there's an old story of doing this. Like 400 years ago, people were, when they thought about mathematics, they were still thinking in terms of describing mathematical concepts in ordinary natural language words. But then this idea got invented of mathematical notation. And suddenly there was kind of a streamlined way to describe what you wanted to do in mathematics. And that was something that really opened up the capability of using mathematics as a way to think about things and a way to communicate about things. And what that led to, the invention of mathematical notation led to the development of algebra and then calculus, and basically led to the creation of kind of the mathematical sciences, which have for several hundred years kind of dominated the approach to doing science and later engineering and so on. Well, in a sense, what we're trying to do with our computational language is to provide a notation for representing things computationally. And that's something that then allows us to kind of think in computational terms, to kind of make our thoughts concrete and computational, and then to build from that. And just as mathematics and mathematical notation built the mathematical sciences, so we can expect that this kind of computational language and the way of representing our thoughts computationally can build kind of the computational X for all fields X, actually not just sciences. Kind of for any field, we can imagine and we can expect a computational version of that field. And I view sort of computational language as a critical piece of making the notion of computation concrete enough that it can actually be applied and built on to create those kinds of approaches to things. And well, it's in order to kind of make this computational language really work, as I say, one has to build a lot of knowledge and essentially intelligence about the world and about things into the language. We have to sort of create this, this repository of computational intelligence that we can then apply in different purposes. Well, it's kind of the, I've kind of view the idea of the sort of computational paradigm and our kind of computational language as a way to make that concrete as kind of the future of thinking about almost everything. And it's, it's a practical thing that's actual software and technology. But more than that, it's sort of a big stack of ideas, which are very powerful and with which people can do amazing things, as many of you well know. So one of the questions that that I'm sort of interested in is, how do we really spread this in the world at large? We have sort of tremendous potential with the computational paradigm and our computational language to unlock new opportunities, both in terms of subject matter and in terms of who has access to that subject matter and those capabilities. And there's sort of a big vision of what we can do with the kind of computational paradigm and computational language. The question is, how do we get there? And what I've kind of increasingly realized is how hard it really is. I mean, this is a big thing that I've realized over the past year from our physics project. It's not one of these things that's just going to happen and quickly. I mean, our physics project, I think if we hadn't had the good fortune to start doing it in the past year, would probably not have happened for 50 years. It's something, I talked about it 20 years ago. I told millions of people about it. Nothing happened for 20 years. I think that we can absolutely expect that nothing would have happened for 50 years, except for kind of a fortunate set of circumstances. And well, if we look at kind of the vision of computational language, which we've steadily been refining over the years, it's some aspects of that we've kind of seen be really absorbed comparatively quickly, but the bigger picture, I think, is still a long way from being absorbed. I mean, it's even something as straightforward as notebooks took about 28 years before it was sort of copied and absorbed, and people said this is now a mainstream thing. But there's a lot more and to understand. And I think one of the things that's been sort of an unfortunate and paradoxical thing is that the further we go in developing this kind of vision of computational language, the faster we can go and the further away we get from what we have readily been able to get absorbed in the world at large. I mean, it's worth realizing that Wolfram Language has now existed for nearly half the time the digital computers have been around. And lots of amazing things have been done with it, including by many people here. But there's an awful lot more that sort of a true absorption of computational language is capable of doing for the world. And I kind of suspect that sort of left to its own devices, we will see the sort of discovery of notebooks type thing happen for many of the other ideas we've had in maybe 50 years, maybe 100, and maybe more. And it's always fun. I mean, I find a lot of fun to kind of bring artifacts from the future in to achieve things today. I mean, I kind of almost see myself as specializing in that, and I encourage other people to do it. It's really a lot of fun. But I think it's kind of a responsibility to the world to have people more generally understand what's possible and to move things forward at faster than sort of an inexorable pace at which it will otherwise happen. I mean, I think that it's kind of like, how should one best kind of move things forward, taking an idea like this and making it practical? Well, the first thing is just build the technology and build it as well as possible. And obviously, I've tried to build the best possible vehicle for doing that. And I'm pleased with what we've been able to build with our company over the past 34 years. I think we've managed to create a kind of rather spectacular engine for innovation. I think we've become, over those years, more and more of an outlier in the technology industry. I mean, we're an independent private company, which many people see as having kind of a simple-minded view of business, in which we kind of make things and sell them at sort of modest, consistent prices to people who use them. I mean, we haven't followed the kind of pretending to give everything away, but make money behind the scenes by some other scheme or something. We've taken a very sort of old-fashioned and simple-minded view of business, which allows us to kind of align the things that we are really trying hard to do in terms of innovation with the kinds of things that that I think our true customers are interested in. Well, having said that, we've been working very hard to sort of make our technology as widely available and accessible as possible, whether it's making, the free Wolfram Alpha website, the cloud basic free site, free Wolfram engine for developers, free Wolfram engine on Raspberry Pis, having site licenses at all major universities, and increasingly being able to having our technology available through other companies and other products, not only intelligent assistants, but also productivity tools and so on. I'll talk a bit more about that later. But for me, I think it's fair to say that our company is mostly a mission, only a business by necessity. I mean, we've tried to sort of optimize everything for innovation, sort of the opposite of most technology companies. Most technology companies, most of the employees are on the commercial side and only a minority are in R&D. We're the exact opposite. Most of our employees are in R&D rather than on the commercial side. But in the end, we kind of see ourselves as creating a seed that for kind of a community to grow with, to help sort of introduce this whole paradigm shift that that sort of computational language can provide to the world at large. I mean, we are definitely trying to do our part, but we need help. I don't think our company is well optimized, as I've said, we're well optimized to create things, to innovate, but we're not optimized to be kind of trying to scale up this process of speeding up the 100-year sort of absorption of ideas. So I think I think that we kind of really need our community to help take these ideas forward. And I know many of you have done lots of things along these lines, which is terrific, but I've sort of realized, particularly this year, and particularly as a result of our physics project, how much more there is to do and how little will happen if we don't really make efforts to get things to happen. It's really it's something that that requires kind of more of an intellectual movement than just what a company like ours, and particularly a company that's really optimized for innovation, can muster. And we're so. The question is, in a sense, how can people help with this? Well, there are things to do at all levels, from the small to the large. Some of them people may not realize are worth doing, and maybe I'll mention a few of them. So, very basic thing. If your organization has a site license for our language, make sure people actually get our technology. Make sure people can actually get our technology. And if there's a problem with that, let us know. And do things like share what you've done with computational language with your coworkers, with other people, with your organization. And when you see people who should be using computational language, tell them that and help them do it. And when you see other software that should be connecting to Wolfram Language, for example, tell the people who make that other software that kind of connection is useful, and tell us as well, and maybe something can actually be made to happen. It's there's a sort of big category of small things, which is to make sure that people actually know that people are using our technology. One of the things that is quite frustrating to see is lots and lots of people use our technology to do lots and lots of kinds of things. Lots of people do wonderful things with our computational language, and they say, well, that's nice, but we don't need to, we're not going to show that to anybody. Maybe they think their code isn't really good enough. Maybe they think something else, but they don't kind of show it to people. But it's really important as a way to kind of spread these ideas, that people know that people are doing things along these lines. For example, it's like list Wolfram Language on your resume. It's an unfortunate thing that people think, oh, I'm using a computational language, I'm using this thing, maybe I'm using it through Mathematica. I learned 3 lines of Java code, so I'll list Java on my resume, but I won't list Wolfram Language on my resume. That's unfortunate. It's unfortunate for us. It's unfortunate for the future. It's unfortunate for the people, and it's a mistake. And it would be nice if people understood that it was a good thing. It's also, people use us all the time to do research. They often don't cite us. They should. It's maybe when Mathematica first came out 31 years ago, it wasn't so obvious what you should do with kind of software and so on. It is obvious today. And people should, when they use our technology in their research papers and so on, they should cite us. In fact, when I was working on the physics project, I decided I'm going to figure out what's a good way to cite our technology and so on. And I realized that individual functions are really a good thing to cite. That's a good way of explaining what you're doing, particularly if you have a piece of computational language right there, showing what's going on. I mean, this kind of show your code is an important idea. This goes along with the kind of, back in the days when mathematical notation was first coming about, some people didn't show their mathematical notation. They wrote what they were talking about in Latin. Nobody can understand it today. Other people actually started using mathematical notation, and that's something which is a transportable idea that other people can really understand. And this is a kind of show your code type encouragement. And just like with mathematical notation, there's better produced code and there's worse produced code. The better produced it is, the better it will communicate to other humans. The computer might not care, but the humans will. But so we're actually making it easier to cite individual functions. Now you'll find on every function page in documentation, you'll find this box showing the sort of standard kinds of citations that exist there. And actually, we're going to do something which we hope people will find useful, which is, if you cite us, we'll cite you, and provide a place for citings of Wolfram Language on the web, which hopefully will lead people to find papers. It turns out, one of my observations is, when you find a paper that does cite Wolfram Language, it's usually one of the really good papers in the particular field that it's about. So I think that our citings database might help people to find those good papers. So it's it's always also disappointing to see places out in the world where we know we have really good things to contribute, and where people just are like, oh, we didn't know that existed. And in a sense, it's fun when you show people that, gosh, we have this thing. Look, we have this website. Look, we have this capability. And people are like, oh, that's really cool. And it's also like, but it would be really nice if people knew about this in general. Like, for example, why aren't we used more in Wikipedia? We have tons of material from our 13,000 free demonstrations, which produce pictures and so on, which we've set up from a licensing point of view so that they can be clipped out and put in Wikipedia, or all of those functions with all their examples and all of the kind of online things that you can do with Wolfram Alpha. Our we just discovered that there's this one guy who's been basically systematically taking down things that people put up about our resources on Wikipedia. It's kind of unfortunate that with our whole community, one guy can basically take down all the stuff that we're putting up. That's the world of, that's the wild west of these things, I suppose. But it's unfortunate, and I think it's not a good statement about what we're seeing in terms of energy from our community. And it's something that, from the point of view of what we're trying to do in creating sort of the seed of innovation behind bringing sort of computational language into the world, it's pretty unfortunate if we don't see, to not feel that we're getting support in those ways. It's, as I say, I think it's both an important responsibility in the world to kind of bring this paradigm that we understand to people. But it's something that is also, as I say, fun to do, whether it's in person explaining stuff to people, whether it's writing papers about how to use computational language, whether it's organizing workshops at professional conferences, whether it's starting a GitHub project with Wolfram Language code and so on, and it's or whether it's by doing bigger things like writing books and so on. I tried to provide a template for how people could easily produce kind of Wolfram language based books, and I think a few people have been doing that, but it's many more could and should. I think it's not so much about writing a book about how to use Wolfram language to do X. It's more about how you can do X using computational language, where the book is really about doing X. And the computational language and Wolfram language and the whole sort of computational language presentation of things is really just a piece of kind of a piece of kind of the exposition of what one's doing, rather than the main focus of what one's doing. The main focus is you're explaining some topic and you're using computational language. It's kind of the future of how to explain things. You're using that as the vehicle for part of your explanation. And by the way, at this point, we're very keen that people use Wolfram language as the term to describe what we're dealing with in our computational language, rather than Mathematica. Mathematica is a great thing, and if you're doing mathematical kinds of things, it's a fine thing to use as a description. But the fact is, that's been one of the things that has been part of the kind of story of, oh, I thought your thing only did math. And as the years have gone by, that's the kind of the concept of computational language and the things we've been trying to do have, I think, expanded far beyond that. And it's important to be able to communicate that and to not have people immediately think, oh, it's math. Math was the last 400 years. Now we've got computational language. That's the next however long. Let's make sure that we can distinguish those things. It is funny because I've been around long enough, fortunately or unfortunately, that I've been able to see how lots of ideas and things have developed in the world. And there are certain things that are just completely inexorable. It could not happen any other way. I mean, this is what I saw with kind of the way that the idea of using simple programs as foundations for models of things, that was inexorable, that would have to be a thing that happened. So it's also inexorable that the whole idea of computational language, the whole ideas about computational essays as ways to explain things, the whole idea of sort of a symbolic representation of the world and so on, this is all completely inexorable. There is no question this is the way things will happen, the whole ideas of symbolic programming and so on. However, left to its own devices, without our community to push it forward, it might take 100 years. But it is it's something that it's nice to know that one is kind of on the right side of history, and that these things will inevitably eventually happen. The fun is to be part of the front lines of actually making them happen, because that's kind of the for most people, this is all sort of ideas from the future, and it's always fun to bring those ideas into the world today, and it's also an opportunity for people to kind of become leaders in this sort of computational future. It's something which many people who are here today know well, and it's something which is sort of a tremendous both personal and organizational opportunity for people, and intellectual opportunity for people to actually establish things in this kind of frontier that I think is sort of inexorably moving in this direction. Okay, well, I said I was going to show you some new technology, and I will get to that. But first, I want to talk about sort of how to access our technology. So let me go back to that. And so there are many ways to kind of access computational language, Wolfram language. Start off with the desktop. There's things like Wolfram Desktop, which is like Mathematica, starts as a desktop thing. It's part of what we call Wolfram 1, which is the kind of the future of how we intend to deliver things. It's a combined desktop and cloud product that lets you access things and use things both directly on your single desktop computer and in the cloud. And sort of the number one kind of access method in that mode of working in the Wolfram 1, Mathematica, Wolfram Desktop, Wolfram Cloud mode of working, the number one sort of method of access is through notebooks. One of the things that we've been working very, very hard on, particularly in the last year, is notebooks in the cloud, giving one kind of a no compromises way to be able to deploy notebooks to the cloud, to be able to take any desktop notebook, whether it's 50 megabytes in size or whatever, and just say publish to cloud, and have that notebook be published on the cloud so anybody anywhere can go and see that notebook just like a web page, except it's not just like a web page because it's got active components and it has sections you can open, 3D pictures you can move around, manipulates you can move, all those kinds of things right there in this sort of free published notebook. And you can also, people can also say, make your own copy, and then they can go into Cloud Basic and they can freely make a copy of your notebook in which they've edited things, and they can save it for up to 60 days through Cloud Basic. I should also mention that when it comes to notebooks in the cloud, another thing that's been developing over the last year is our notebook embedder, which allows you to take a notebook and embed it in a web page. And so that's, for example, in Community, I think there are now 1,000 notebooks that have been posted that way, that are embedded notebooks embedded within Community posts and so on. But in general, Notebook Embedder is a good way to take notebook content and just put it on any website. You publish the notebook to the cloud, and then you just use Notebook Embedder to bring the notebook onto any website. It's a more flexible way to do that than to use things like iframes and so on. So you can, let me maybe show you an example of that workflow. Let's see. Okay, what do we have here? What is this? This is some giant notebook. This is, I think, a working notebook from some physics session that we did. So let me take this notebook and just show you what what's involved in publishing it to the cloud. So I just go to this menu item and I say publish to cloud, and it will go and eventually, okay, let's say automatically assign a URL. Let's now say publish that. Okay, I think this is a reasonably big notebook, so it might take a little while. Let's it, oops, did I need to enable dynamics there? I don't know. Oh, I probably needed to do that because otherwise it can't format it to be able to save it. There we go. Okay, so now it's now putting it in the cloud, and there it is. It's now in the cloud. There's that's kind of cute thing. You can there's a QR code that's useful if you're giving a lecture or something, and you take the notebook that you've used and you say, now I'm going to push it to the cloud, and then everybody can get out their phones and just read in that QR code and be able to immediately get that notebook up in the cloud in a web browser on their phones, and they'll be able to browse that notebook. So now if we go there, let's go see that notebook. We can go and view it in the cloud. So now we'll be just going to the cloud, and this is now the published version of that notebook, and we can go down and look through it. And all these things are now actual pieces of graphics that we can do all kinds of things to if we want to. And now if we want to, we can now say, create your own copy here. I could say download, and I could look at it using Notebook Player, for example, on a desktop machine, or I could say make your own copy, and now it will make a copy in the cloud. Oh boy, I didn't log in on this machine. There we go. Okay, there I am. And this is oh, interesting. let's see. No, I don't need to remember it. Okay, so now this will now be a copy of that notebook that's been made for me, and it has everything. Everything now here is editable, so I can go and I could probably, well, actually, this is a function that is not globally defined, so I have to go and okay, so it's now, but now I can do any computation I want with this. I could go here and I could just say, you know, what's 2 + 2, and it will now, this will now be an active notebook in which I can do computations. So this is kind of the workflow that's possible now, is to go from a desktop notebook, there we go, to, if I waited a little bit longer, the way this works is when you push a notebook to the cloud, it is making an HTML cache of that notebook. And when the notebook comes up, the first thing you see is the HTML cache. Sometimes if you, it's a little bit shamanistic, but sometimes if you wait a bit longer, the HTML cache will have been created, and so the notebook will come up instantly. If you ask to see it very impatiently, it will still be creating that HTML cache, or it'll have to just render from afresh without having a cache when you first bring it up. But okay, there it is. So this is kind of the workflow of, you create a notebook, you can create it in the cloud, you can create it on the desktop. If I have this one in the cloud, I could say here, just publish this, and that will now go through the same kind of dialogue to publish this cloud created notebook as a published notebook in the cloud. And the rules are, anybody can see a published notebook in the cloud unless you set it to be something that has limited permissions. So in any case, that's if you want to, you can control access to that notebook. There's an elaborate system for controlling permissions and so on. But by default, you publish a notebook and it's visible to everybody in the world and runnable by everybody in the world. So that's kind of a bigger story when it comes to what you're dealing with here is our public cloud, the main Wolfram cloud. We also make available private versions of our cloud, enterprise private cloud product that allows people to set up their own notebook serving private clouds on their own infrastructure or in cloud providers' infrastructure. So that's one of the things that, so all of the stuff that I'm showing you about the desktop, the cloud, you can interact not only with our public cloud, but also with private clouds, which will have the same capabilities as our public cloud. Well, so we're doing lots of different kinds of things here, but one of the things that I thought I might show you is a new kind of direction. Let me see if I can bring this up here. A new direction that is using both in desktop and cloud, which is a thing we call Wolfram Alpha Notebook Edition, which is kind of a combination of Wolfram Alpha and Wolfram Language and Wolfram Notebooks. And so the idea is, this is something initially aimed primarily at education, where the concept is that you get to give your input as in pure natural language. So there's nothing you have to learn. So I could just say here, integrate log x times sine x or something, and this will now get interpreted using our natural language understanding system. What you'll get is then a piece of Wolfram language code, which you can then evaluate. Or I could go on and I could say something like, what is the density of tungsten? And I should get a result there that I can then compute with. And so what's interesting about this is that you can immediately sort of walk up to it, and just like Wolfram Alpha, you can start working with it, but then you can build up progressive computation. So back here, if I go up here, I might say, let's try this again, and let's just get result again. And now it would say something like, let's go and say, let's look at related computations. Okay, plot, function, and integral. Okay, let's do that. And so we get all of this, it kind of guides us through being able to do different kinds of computations, but we can take we can build things up in a way that is not possible in Wolfram Alpha on its own, for example. We can build things up just like we could in Mathematica or in Wolfram Language. So this is now available on desktops. It is soon going to be available also in the cloud. So people can just go to their web browsers anywhere and start, just like they can interact with Wolfram Alpha, they can interact with Wolfram Alpha Notebook Edition, but now they're building up sort of full computations that they can do things with and that they can turn into presentations. People can do all sorts of educational things with this. As I mentioned, we now have site licenses at pretty much every major university in the world. One of the things we're doing to support that is to introduce single sign-on capabilities for our ID system. And that's just been rolling out in the past few weeks. A bunch of universities have already rather rapidly got their systems hooked up to our SSO capabilities. And that's something that we hope to get very broadly rolled out over the next few months. Something to encourage your university to do is to get signed up with the SSO system so that people can immediately use their university login credentials rather than Wolfram IDs to get access to all of these things. Talking of notebooks, by the way, it's worth remembering our notebook player on iOS. We've had now for a couple of years the capability of running a native Wolfram Language kernel directly on an iOS device like an iPad or an iPhone. That means that you can take a notebook and you can run it at sort of full speed without ever having to interact with the cloud directly on that iOS device. I mean, I use this capability all the time because people send me notebooks in email and I can now just open them directly on my phone and interact with them there. And that's a very convenient thing. And it's something where in educational settings where people have lots of iPads, it's something very convenient where you can just send a bunch of demonstrations, a bunch of manipulates to the iPads and have them run that way. Okay. Well, notebooks are a great mechanism for doing things, but sort of how else can you interact with Wolfram Language? Another big category is through APIs, by having programs call Wolfram Language on servers and so on. So as you may know, one of the things we've had for many years now is instant APIs, where you can just take any piece of Wolfram Language code and you can just say cloud deploy an API function of that piece of code, and immediately you've got this running web API that exists that can run that Wolfram Language code from anywhere. And we've been gradually providing more and more capabilities around that. Last year, we introduced the client library for Python, so you can just take you can basically treat all of Wolfram Language as a giant library. You can kind of add computational language to the Python programming language, so to speak, by just using this client library and by just using Wolfram Language directly from within Python. And that's working by using API, both in the cloud and on the desktop. Behind the API, you can have either a public cloud, either using our public cloud, you can use a private cloud. There's a new thing that's coming, which will be available, which is already available in beta test form, which is called Wolfram Application Server. Wolfram Application Server is a pure API server for Wolfram Language, and it's something that it's delivered in containers, Docker containers, Kubernetes things, and it's also something that you can cluster. It's available both as something that you can run in your own infrastructure and something you can just get in AWS or Azure container and a container in a virtual machine there to run the Wolfram Application Server. And what it does is it allows you to execute Wolfram Language APIs. So it doesn't have all of the notebook delivery capabilities. It doesn't have all of the authentication capabilities, all of the kind of management capabilities of a private cloud, but it just has the ability to serve APIs. And that's something where if you're building a website, you're building kind of internal microservices, whatever, it's a really convenient way to deliver that is to just have a Wolfram Application Server put your code, you can directly communicate with it from a desktop Wolfram language or a cloud Wolfram language. You just say, push this piece of code to the application server. Now it becomes an API that everybody can access. We've also, the application server also allows you to serve web forms of the same kind that, that you can serve through our cloud. Well, there are many other interfaces. A big focus that we have these days is embedding our technology inside lots of other kinds of systems in the world and making it possible to have our language be something that I had various things I was going to bring up here, but I didn't do it. To have our language be something that one can access as a piece of other systems that one is using. And so, for example, it's sort of a general piece of our strategy of sort of delivering computational intelligence everywhere. I mean, I guess my vision of these things is the following: that sort of back in the ancient past, when there were first computers, when I was first using computers, it was just a raw computer. It didn't have languages, didn't have an operating system. Eventually, one got to sort of take for granted the idea that a computer would come with an operating system. Later, that it would come with networking capabilities or come with a user interface or whatever else. It's kind of my vision that that in not too long, one will be able to sort of expect that computational intelligence, the kind of thing we have in our computational language, will be something that you can just sort of take for granted when you walk up to a computer. And we're seeing that happening through an increasing number of kind of ways in which our language and our is getting integrated with systems out in the world. So, for example, the list of things that sort of our computational language powers is not too shabby already. I mean, things like Siri and Alexa use our computational knowledge. We're sort of the only provider of this kind of computational knowledge in the world. So it's sort of not in a sense too surprising, but it's nice to see that that's a place where millions of people get access to what we built every day. Another major sort of piece of embedding that's coming soon is with Microsoft. You'll see this is an example of integration into Excel, of being able to take the kind of computational knowledge that exists in Wolfram Alpha and be able to immediately populate an Excel spreadsheet with it, and lots of other kinds of things with Wolfram Language planned as well. So it's, I mean, this is kind of the beginning of a strategy with Apple and Amazon and Microsoft, actually one other large partner to be announced soon, of using our computational intelligence as a sort of unique source of computational intelligence in a variety of products that are very widely used. And so there's sort of a question then, if you're, whenever you sort of are using some system out in the world, could that system be kind of supercharged by adding computational intelligence with our language and so on? And if so, tell whoever makes it, tell us, bring us together. We'd like to see this happen. I think that whether that's a specialized engineering piece of software that needs to make use of our capabilities to know about real world kinds of things, to do natural language understanding, to do analytics, to do geometry, whatever else, whether it's some kind of educational system, whether it's some kind of piece of middleware that needs that instant API to make it easy to do all kinds of things, can it have Wolfram language embedded? And we now have the technology to embed in almost anything. We just need kind of the bandwidth to make the deals to make that happen. I should talk about kind of non-cloud places where Wolfram language gets deployed. I mean, there's hardware things like Raspberry Pi, where we're basically just part of the operating system. We also have our Wolfram engine for developers, and we're trying to make sure that this is available through sort of every conceivable package manager and that you can download it anywhere you want. This is intended to be free for development and licensed for deployment when one comes to that point. And so as I say, we want to make our language as ubiquitously available as possible, so people can kind of take for granted that they can get it. We also want to make it so that people can redistribute Wolfram Engine easily inside other products, even open source products. We have a mechanism for letting people distribute Wolfram Engine as part of an open source project. And that's something that just to help this process of making sure that the things we built and that this kind of paradigm we're pushing is capable of being deployed as widely as possible. We basically don't ever want something about the way that we license products, or that we have to license things from upstream providers of data and all those kinds of things, to get in the way of letting people have access to what we've done. I mean, we've solved this problem at universities and labs and so on. We will solve it for embedded Wolfram engines. We definitely haven't seen all possible cases of embedded Wolfram engines, because Wolfram Engine has only been out for a year or so, but we're committed to solving that in all of these places. I might mention that one new thing that's happening is there is a new persistent Wolfram engine. So normally, if you have a Wolfram engine, you launch it, it just runs, it does its job, it stops. There's a new thing called WSTP server, which is a persistent Wolfram engine, which kind of sits as a daemon-like process on your computer and can spawn Wolfram engines that that can do computations for you, and it can maintain a persistent Wolfram engine if you want to, so that you can maintain state between different computations and so on. So I mean, there are just many different ways to deploy language. If you look at kind of the deployment options, it's getting a little bit quite a range. I mean, there's at the server level, there's Wolfram Cloud, which allows you to deploy notebooks and APIs and scheduled tasks and all those kinds of things. There's Enterprise Private Cloud, same set of capabilities. There's Application Server, which is for deploying APIs. There's the this is a very lightweight direct deployment of a Wolfram engine along with a web server. There's yet even more lightweight deployment with a web server, and so on. And then there's WSTP server that I just mentioned. So these are all sort of for different sizes and shapes of deployments. These are all ways to deploy Wolfram language in various kinds of systems. Well, it's all rather complicated, and it's complicated because the world's complicated, and there are all kinds of different places where one can potentially insert our computational language and so on. One of the things we're working hard on is to sort of harmonize all these pieces into what we call our hyperarchitecture, to sort of make it so all these different components can be added however one wants. It's sort of the goal is to design our deployment space so that it's really convenient, design sort of deployment, the space of deployments, as we've designed the space of functions in our language. And that's what this hyperarchitecture concept is about. By the way, another emerging kind of deployment is autonomous deployment of Wolfram language in things like blockchains. So we have this operation called Wolfram Blockchain Labs, which has been involved with connecting Wolfram language to lots of kinds of blockchains. It's also emerging as quite a standard for blockchain education. It's very convenient to study and use blockchains from within Wolfram language. The biggest story, though, is the emerging idea of computational contracts, where we're kind of writing contracts directly in Wolfram language, and we're using our source of computational knowledge to provide sort of facts from the world for the operation of these contracts. And so that's something which is sort of an emerging autonomous use of Wolfram language as something which just sort of autonomously exists in the blockchain world as a piece of computational language to be executed when a contract is triggered, so to speak. Well, there are just all sorts of other deployments. I mean, here's just a random example. This is a registry of notable universes. This is just a cloud deployment of Wolfram language. There's an embedded cloud notebook there that is about well, this particular universe model, which I doubt will be the one, but it's one of them. Here's another example. This is a project we've been doing for the Museum of Math in Manhattan. This is a project to kind of collect together lots of interesting artifacts from the history of mathematics, and to, I don't know which one to pick, but I'll pick one of them, and to also provide, okay, that one was a coming soon, and to also provide computational essays that kind of describe the what was going on, let's say, the Rhine Papyrus or something. There we go. There's kind of a, and this is all just embedded notebooks as part of these web pages. Also, another deployment is all of the MOOCs that we've been building, and we've got an increasing number of courses, both about a variety of kinds of subject matter, whether it's data science or calculus or whatever else, built using our course authoring platform, which we will eventually make broadly available, but people can request it even now. We're kind of trying to build up a sort of a whole ecosystem around what we're doing that includes things like our notebook archive, our function repository, our data repository. I'll probably talk about those a little bit more later. We're also, in addition to trying to build software, we're also developing further our services efforts. So people who say, I just want to get something that works and I want to build it with our technology. There's both our technical services to implement something specific, and there's Wolfram Solutions, which is concerned with architecting sort of a whole solution. And they've been doing a lot of that for all sorts of Fortune 50 companies, building sort of from the future type solutions using the technology that we have. They're also, those are sort of, I consider these kind of on-ramps for the use of our technology in a bunch of different places. There are some much more personal on-ramps, things like our summer school. There's some projects from our summer school this year. There's definitely some physics-themed ones there, or our summer camp for high school students. Also some projects from this year here. Well, so we're also trying to develop kind of an office hours mechanism for people from the community to interact in a good way with our internal team and our R&D staff and so on. That will be something that's coming online soon. We also, for people who are doing startups and so on, we have a new thing we call our Wolfram Eureka program, which is kind of a pre-incubator kind of educational program for people who want to kind of understand our way of being able to develop products and doing innovation and how that turns into companies. And that's something, again, we can people can find out about from us. And in terms of sort of on-ramps and interaction, don't forget our live streams. I've been doing that almost every day, live streaming kind of our internal design meetings and so on. It's a very, it provides a very sort of open, transparent way for us to interact with people and get feedback and so on. Also mentioned, by the way, our open bug tracking system, which I know quite a few people here have been making use of, and we will be doing more live streams related to that soon. All right, I guess it is demo time. Let me, I've been talking about all sorts of general things. Let's look at some actual, what's coming in 12.2. So let me see here. Let me just save this someplace where I'm, before I mess that up. And let me just, oops. There we go. All right. So, okay, what's coming in 12.2? Well, the first big area that I mentioned earlier is video. So if I have a video, see what video this is. That's being read just for, that's just a file name. Okay, so this is a video from the 2009 technology conference. And
I know some of you have come to
you
many
can actually
conferences
play the
with
video
us, but,
directly in the
particularly for those who are new here today, I thought I would say.
So that's what a video in a notebook looks like. Just like we can have images in a notebook, so now we can also have videos in a notebook. but now this video thing, we can compute with it. So for example, I can say, get me 10 frames from that video, okay? So now it'll just get me 10 frames as images from that video, okay? And that those, or I could say something like, let me take that video and let me make a video time series map, and let me try and compute the mean value of the RGB components. Okay, it's going to take a little while because videos are big. Grind, grind, grind. And okay, let's see what we can do here. Let's make a date list plot with red, green, blue here. And this is now going to show me as a function of position in that video what the average colors were in those images. Okay, so this is now operating on videos as we can operate on all sorts of kinds of things. And if we wanted to, for example, we could slice out let's say we could just go down here and we could slice out the audio from that video. I don't know how long this will take, but just take that audio. Let's see what happens. This is reversing it. Proto-Indo-European. But anyway, that was the result of just taking the audio as another object from that video and doing a computation on it. So we can also do something like, I can do all sorts of more elaborate things. Let's see, I might have another one here. Let's see if we can do this. Let's see, this is doing a video map. That is, let's see whether this can be done in a reasonable time. Oh, did something. All right, let's see what happens here. Let's just see, we can now it'll open that one in a separate viewer. Let's see if we can do this. So what this will do, oh, that was boring. It was quite boring. All I did there was I just blended every 5 seconds of the video together. Kind of like everything was ghosted out there. Didn't look that exciting. But I could as well have done a video map with some kind of machine learning thing and done face recognition on each frame, all those kinds of good things, or done that with a time series map. Or I could just take some random manipulate here. Let's try this. Okay, so here we have some random little manipulate that I made that's 1 line long. And now let's see what happens if I just say make a video of that manipulate. And I probably could have, let's see, that this is probably grinding. It might take a long time because it's actually taking a while to render each frame. But the main point is that this will now create a regular sort of maximal efficiency video with all kinds of codecs that you can then embed on a website or anything else directly from a manipulate like that. I think I should not finish this here. Let's okay. So let's keep going. So then another thing that's new in 12.2, and but by the way, I should explain that what I'm showing you is obviously a prototype version of 12.2, so all kinds of things may go horribly wrong here. This is just an animated image. So it's kind of a junior video, but it's now something you can immediately and directly include in notebooks. And this is just coming from a PNG file, an animated PNG. Okay, well, let's talk about user interface. Here's something interesting that we decided to add. When you type in math, we've got lots of wonderful capabilities for typing in math that means something to the system. But sometimes you just want to type math that doesn't really mean anything, just like you want to type text that doesn't have direct computational meaning. One thing we've now added is the capability of just typing in tech, for example. So if I type control $, and then I type, let's say, \frac, let's see, 1/x. And then now this is a piece of input that was just given in tech. Now this particular one was given in an input cell, and it in fact can be interpreted as a piece of valid Wolfram language input. But we can also just input, in a sense, meaningless math. And if we're making, this is text, and now we start off with a piece of meaningless math here. And let's say I could say \mathfrac SON. Let's try that. Okay, well, that wasn't very exciting. I would have expected that to do something more interesting. Let's do something more interesting now. Let's just put in, here, let me see if I can do control $. Let me try this. I'm not sure if this is going to work. Okay, maybe that will work. Okay, that's a big lump of tech. Let's see what that does. Okay, so now that's then rendered that text directly as a piece of sort of meaningless math as part of the text that I've got there. So you can see it there. So this is something I think will be very convenient for people who, in a sense, want to write narrative math that doesn't yet have computational meaning. Okay, another thing that is, again, sort of a straightforward convenience is auto-linking of hyperlinks. And actually coming with that is the ability to, we have a new hyperlink dialog, which has all kinds of convenient ergonomic features relevant to linking to notebooks as well as linking to things on the web. Another thing that we have, which I have to show you in a prototype of the prototype. Let's see if I can bring this up here. Okay, there we go. Is a new capability, which actually is something we've had for a few years in documentation and so on. It is the idea of click to copy. So if I say click to copy of something like, I don't know, x to the fifth or something, now I have something that says x to the fifth. As I hover over it, I get a thing that says copy to clipboard. I click it. If I now go here and I paste it, it will have that in the mouse, so to speak. So click to copy is something which is actually a default for some pieces of published notebooks in the cloud. It's a default for some of our documentation, but now it's something you can also have in any notebook that you produce. Okay, let's go back to something a bit more computational. Let's talk about a different area. Let's talk about a new thing that we're bringing in, which is spatial statistics. So turns out there's this idea, we've got statistics of things in time, like time series and so on. We've also got the idea of spatial statistics, of things in space that can be treated statistically. So let's say this is spatial point data, 300 random points in 2 dimensions. And we can ask things like, what's the mean point density there? Okay, so it's just some number. Or we can say, what's the point density function? And now we'll get something which is an actual function that is the function that represents the density of these randomly chosen points. So for example, we could say, just make me a 3D plot of that density function. Now that's the density function of those random 3D random points. Or I could say, let's compute the pair correlation function of those points. So now this is computing correlations between all of those pairs of points. If we now say, now let's plot that pair correlation function as a function of distance, this particular one won't be all that exciting. It's just, okay, it's just showing that the pair correlation is close to 1 for these particular points. But this is now allowing you to essentially take spatial data, positions of things, and do computations with that. And now, let's see, we could take, let's take another example. We can, this kind of thing works not only for abstract points, but also for points in I'm surprised that that's still blue. Okay, for points in actual geographical points. Okay, so what we did here was we got spatial point data of some data about U.S. national parks, and there when we said what's make a point. What is this? This is some strange bug. Oh dear. Okay, well that's okay. I was showing you that's what I get for running a prototype build. I thought this okay, there we go. So now if we wanted to, we could take the whole idea of random processes applies as well to spatial data as it does to standard distributions like a normal distribution or something. This is now a point process. And so now this is saying, let's get that geographic point process. And we've chosen points now over the US that are picked according to this particular statistical distribution of spatial statistical distribution. Okay, so that's a new thing is spatial statistics. Lots of interesting things there. While we're talking about geo, we have not only sort of merging geometry with geography, but also merging topology with geography, a kind of geotopology. And so we've got all kinds of issues like, let's say we pick a bunch of points. which can be in lat long space. And now we can do things like say, what's a polygon inside a polygon inside a polygon geographically? And yes, you know, the country of San Marino is important because it's a hole in Italy and so on. But this is a general kind of thing where we can deal with sort of arbitrary topology of insideness in geographic computation. Okay, another thing in geographic computation, big thing actually, which we've been working on for quite a few years, is to make our maps be made with vector graphics. So this is running on a very slow test server. Real soon now it'll be running on a wonderfully fast server, but right now it's running on something really, really slow. So it's going to take it a while to load this. But what we should see here, I hope it's going to load it. Come now. Oh, there we go, finally. Okay, so what's important about this is vector graphics. And we computed every placement of every label here. And as we go in, and I don't know what this stupid bug is, as we go in, we can zoom in on this, and we'll find that this is sort of perfect vector graphics, not something that has finite resolution. So that's an important piece of technology, and actually you'll see a bunch of things coming out with maps from us that make use of a bunch of algorithms that we have for things like label placement and so on. Also, many different styles of maps are coming. I don't know if I've got one other example here. Let's see if we've got one more example. This is just a different style. Let's see if that comes up at a better speed. We've got a variety of themes for, okay, that was just a more web-friendly version of styling for maps. But now you can expect kind of no compromises, arbitrarily high-resolution maps from Wolfram Language. Okay, other kinds of things. So from space to time, in our theory of physics, we've realized that space and time are a bit more different than one might have expected before. But regardless of that, it turns out that just like there are datums to represent different coordinate systems that one can use to label points on the Earth, so there are different kinds of ways to label moments in time. And one thing we've been adding is lots of new calendars to represent different kinds of ways to represent moments in time. And so here, for example, if I say what's now in lots of different calendars, and we can see, it might take a little while to compute some of these because it has to compute actual astronomical facts. And so here we have, I don't know what some of these are, in Japanese calendar or the Ethiopic calendar and so on. We have all of these different essentially datums to represent time now available in the system. Well, oh, and we can do lots of other kinds of time computations, lots of new time computations. So, for example, in the US, it's it's a big deal that it's an election time. But a question you might ask is, when is election day? And so here, that's the algorithmic version of when election day is. And now we can say, do a date select over the years 2020 to 2200 of what days elections would be held on according to this formula going up to 2200. And that's now another sort of thing we're able to make computable in the world, is these kinds of computations about dates and so on. All right, let's talk about core math kinds of things. Something we've added is a lot of capabilities for sort of reasoning about functions. So here's function singularities, looking at the singularities of this function over the complex plane. We've also, these are sort of properties of functions that end up being used all over the place. Another thing we've done is we're continuing to add yet more mathematical physics special functions. This is a Lamé function, which is by now is a 4-argument, very complicated kind of function. Now, sometimes, when you think, oh, these are just obscure special functions, why would one care about them? Turns out that they're important in all kinds of places. Like here's, for example, a particular geoprojection that just got unbelievably much faster than it was before because we sped up the evaluation of Jacobi elliptic functions. So, okay, another core mathematical thing, inverse Laplace transforms, adding Bromwich contours. integration as a way of doing many more inverse Laplace transforms. You see a result there that comes out in terms of an inactivated sum. I could say activate that sum, and then I could say let's go ahead and plot that, and we see the various poles being in or out of the contour as we compute that inverse Laplace transform. Okay, when talking about math, we've also been adding to our whole way of dealing with sort of raw axiomatic systems. This is an axiom for implicational calculus, and the idea here is to be able to deal at a completely formal level. It's sort of the more symbolic than just symbolic way of dealing formally with systems. And we also have our automated theorem proving capabilities, which have been progressively expanding. One thing that's happened in the physics project is we have become very industrial users of automated theorem proving. In fact, for example, the recent efforts in proving equivalence to categorical quantum mechanics are really an adventure in automated theorem proving. It's kind of a nice thing to be able to say, yes, we actually proved that our model is equivalent to this. And by proved, I mean, here's a proof as an actual piece of computable data. Well, so, oh yeah, talking about proofs, we could talk about sort of the place where that technology first started to be used a lot, which is in Euclid and Euclidean geometry. I actually just wrote this blog post last week, I think, about the empirical, if this comes up, oh, come now. Yeah, there we go. About the empirical metamathematics of Euclid. There's kind of a study of, that's an example of theorem proving in our system, but then I was studying kind of the network of definitions that, that Euclid made in his 465 theorems, and we're studying kind of the graph of dependency. This is kind of a piece of empirical metamathematics that I'm interested in doing because I'm interested in the general theory of metamathematical space. And this is kind of a first example of that. We've also looked at, I also looked at all kinds of, well, I found that somebody had done part of what I did 400 years ago. Don Knuth actually pointed this out to me. They almost did a little piece of what I did with dependency graphs for Euclid, although they didn't get it quite right in 1600. But in any case, also looking at some other large formalized mathematics data sets and trying to understand sort of the overall structure of metamathematical space. But back to Euclid, one of the things that we've done is to add more to our capability for dealing with Euclid-style geometry. So this is a way of representing not just a geometric object, but a geometric construction directly in Wolfram language. So this is a way of making computable the process of a kind of Euclid-style deduction. And so this is kind of an algebraic version of that Euclid-style deduction. Here's now an actual instance of the deduction. Why is it doing that? Well, that's what I get for running this prototype build. Why is it not coming up? Well, it's a dynamic thing. Come on, it should work. Okay, well, it should be showing you a nice picture of a Euclid construction here, but for some reason it is not. That's unfortunate. Okay, well, we have to say abort that. That's going to cause all kinds of trouble. Let me see. What is it doing? It's gone crazy. All right, let's see whether I can get this to work. If I go here and I say, what happens if I say paste complete geometric scene? I wonder what that will do. No, that didn't do anything. All right, let's try this one more time here. Let's try computing this. Let's try this again. And let's go back up here and tell it to enable dynamic updating. Let's try one more time. Oh, wait a minute, something happened there. There we go. Who knows what was happening there? In any case, we can take this Euclid, we can take this construction, we can actually interactively move around the points in this construction. There's another important new thing, is the ability to sort of interactively draw on the scene, and we can go through the construction here. We can go and look at different steps in the construction. Actually, I messed things up here. Let's see if I can, how do I get this? Maybe I can revert it here. Okay, so this is that stage in the construction. I can move that B around a little bit, can move it to there. I can move forward in the construction, and I can eventually get, in this case, a quadrilateral triangle constructed. So this is kind of making use of our dynamic interactivity together with our ability to represent symbolically this kind of synthetic geometry, together with, under the hood, a lot of very elaborate algebraic computation to make all this stuff work. Okay, so let's see, moving on from there. We're talking about computational kinds of things. Here's a new area where we're kind of applying computation, and that's in biosequences. So here, for example, if I do this, I will get something which is essentially a symbolic representation. And what is going wrong here? This is very, okay. This is kind of a symbolic representation of a DNA sequence. And so I can do things like I could say, biosequence translate this. And so then it'll take that DNA sequence and translate it to peptides. Oh, isn't that cute? Or I could say something like, let's take a biosequence for this particular gene. And now I'll go and I'll be looking up that gene in the human genome. I can get the biosequence for it. I could, for example, just say string reverse this, and then I'll get the reversed sequence, or I could say biosequence complement that. I get the complementary sequence there, and I could then start doing computations on this. So I could say, what's the molecular mass of that particular piece of DNA? Or I could say, I could do something like this. I could say biosequence translate this peptide back into those are the possible DNA sequences that would generate that peptide. Or I could say something like, let's take the biosequence that comes from that's a little small piece of DNA. Let's make an actual molecule out of that. And of course, everything fits together. And we can now say, given that molecule, let's see whether we can do this. Let's try and make a 3D plot, a 3D rendering of that molecule. And now we have that piece of that little tiny fragment of DNA. And now we've got an actual 3D molecule that's generated from that. So I mean, it's kind of a question of, oh, isn't it a little bit crazy to have something like biosequence translate as a function in the language? Well, no, it's not, because you know what? All users of this language right now are humans, ultimately, although in intermediate stages, it's definitely used by computers. And for us humans, we're biological organisms, and biosequence translation is something that is universally applicable to us. So it's something that makes perfect sense to have in our computational language to represent things in the world. But it's kind of really nice to see how both our string computation capabilities and our chemical computation capabilities sort of come together in this kind of biosequence capabilities area. Okay, talking of chemistry, let me show you another new thing. This is let's just draw a molecule. Okay, so this is now a molecular drawing palette, so I can go and I can start clicking, and I can just start drawing a molecule. I'm not very good at this. I don't really know much about molecules, but anyway, let's say I say show hydrogens. Okay, it'll show me where the hydrogens are. Now I can say return that. Okay, now I have a molecule. I can again just say make a molecule plot 3D of that. And now I can take that molecule that I just drew, and now I can get this 3D molecular structure, and I can compute all sorts of things about the molecule. Talking of drawing, here's another thing. After many years, we've built a whole sort of new drawing system for Wolfram Language. So you can say canvas, and you get up this canvas that hopefully when I click on it, see if this comes to life, that should give us an attached cell here, which contains drawing tools. And you'll see these are very nice new drawing tools that allow us to, if I know what I'm doing, what do I do here? Oh no, what am I doing here? Maybe I need that. Okay, so let's say I start drawing things, and I can conveniently select these things, and I can make it thicker or whatever. The main point is that we have all these capabilities directly in the language. And in fact, we have it set up so that not only can you draw from scratch and create something that is now a computable drawing, you can also take something like take an existing graphic, and you can start annotating that existing graphic, and you could add some region there. see what we add here. This now becomes an overlay on one's graphic. And so if I evaluate this, I'll get something which is an overlay where I can actually be changing the underlying graphic. It could be a manipulator or anything else I want. And this is now a sort of overlay annotation on it. Okay, talking about graphics. Another thing I should say is that this notion of attached cells, this thing down here is an attached cell. We have a new function, AttachCell, which is an actual user level way of manipulating notebook objects to attach cells to things. Okay, other graphics kinds of things. New thing, radial axis plot, otherwise known as a radar plot or a spider plot or a star plot. Nice and general here. Another one, a parallel axis plot, also having lots of other names. This is something that is just convenient for dealing with highly multivariate data. Okay, another thing we've got is array plot 3D. This is a function I've long been waiting for. So that I'm running a game of life cellular automaton, and I'm running it in 3D, and you can see all those little structures that come out. But this is now array plot 3D is the thing that's creating this this graphic with that that periodic structure there and so on. And actually, this is to show you something that this is just to manipulate with a 3D cellular automaton. I first made these pictures of this particular thing with a Cray 1 computer sometime in the early 1980s. And it's really kind of nice to see that I can just sort of interactively make them by just running a slider now using ArrayPlot 3D. Okay, so let's talk about styling of graphics. Something that came late in the 12.1 cycle was the idea of cross-hatching. It's kind of a thing where if you want to make really sort of elegant drawings of things, it's often useful to have these kind of filling patterns. So now we have that. Something we're adding in 12.1 is different kinds of filling patterns. Like this is a conic gradient filling that allows us to fill like that. These are just other kinds of things of that kind. Okay, more computational kinds of things. Lots of things in machine learning. A lot has been added to our neural net repository. A lot of new kinds of networks added here, which we can directly use in Wolfram Language through NetModel. We've also been building a variety of new layers to support the new kinds of things we've been adding. One new layer is a thing called function layer, which provides direct access to kind of the low-level infrastructure of neural networks through the MXNet layer that we have. Another thing we've been adding is compiled layer, which allows one to use the Wolfram Language compiler to actually create direct machine code that can be inserted into a layer in our neural net framework. Another thing we've done is to support export to the ONNX framework, and that allows one to do things like build a completely standalone, oh wow, what is this? That is very odd. Okay, to build a completely standalone version of a neural net that can be, for example, and the thing I was trying to show you, which came up as a notebook, was I thought going to be a cloud document that is an example just recently done of taking a neural net that was created in Wolfram Language and deploying it directly to the machine learning framework on an iPhone. So it's something where you can develop in Wolfram Language and then deploy to a device like an iPhone as a native piece of machine learning code. I should remind people that we have a whole variety of ways in which we can kind of deploy native code to things. Something that just got added in this version of Wolfram Language is for our microcontroller kit. We also can deploy to sort of all species of Auduinos now. I think there are 36 new kinds of targets where you can take a piece of control systems, symbolically represented functionality in Wolfram Language, and compile it down to something that can be run in an independently running microcontroller in a device, for example, completely independent of Wolfram Language. So, okay, let's turn to I should say that also in machine learning, lots of other things being added, steadily improving all sorts of super functions. One that got added is face recognize. We've also so that's a thing to say. I mean, neural nets are a big sort of framework kind of thing. They're kind of one of a series of big frameworks that have come into almost numerical computing over the years. First, there was linear algebra. Now there's neural networks. Somewhere in the middle there, where there was optimization, and particularly things like linear optimization and then convex optimization. We made a big push to provide kind of industrial strength convex optimization in Wolfram Language. We've extended that in version 12.2 to add complex variables and parametric convex optimization. We also added the capability to connect to other external optimization libraries directly from Wolfram Language. Well, now something else that we've been building towards for about a decade is real-world PDEs. So we've had the capability to do numerical PDE solving, and we built finite element methods and so on. But this is kind of a way of constructing sort of physical models with PDEs easily. So this is kind of a construction element, a Laplacian PDE term. And there are all sorts of different PDE terms and so on. But here, for example, we're saying, let's do the eigenvalues. Let's find the eigenvalues of a Laplacian PDE term over a regular polygon that happens to be a pentagon. And so now if I can say, let's make a list plot of those, this is going to show us the eigenmodes of a pentagon. And it's showing us, probably we can figure out the symmetries of a pentagon from looking at the degeneracies of those eigenmodes. So let's see what we can do here. Let's see if we take this, let's do something more ambitious. Let's say we have a geometry represented by that region there. And now let's say we want to actually do let's say that's a muffler. And let's say we want to actually do a physical computation about something to do with that muffler. Okay, well, let's use our knowledge of actual physical things. Let's find using thermodynamic data, which we actually just extended in this version to include more with humidity and other kinds of things about air and so on. But we can just compute these things about the real world. Now we can define these variables to represent the actual sort of physics of our muffler. And now let's say we actually set things up with acoustic PDE components and acoustic absorbing values. Those are part of our sort of library of building blocks for sort of physically oriented PDEs. And now, for example, we can do a parametric solution to that PDE with the region being that muffler. And now we could even go ahead and make a slice contour plot 3D of that particular solution at some particular frequency in that system. Or maybe we can go on and what's this? We could go on and compute the sort of frequency response of the muffler by actually solving the PDE, solving the Helmholtz equation with these boundary conditions. And it's just going through and computing. That might take a little while here. It's computing the result there, and it's going to give us a frequency response curve, hopefully at the end of this. So it's something we've been building up to for a long time. It involves a lot of computational geometry, a lot of linear algebra, a lot of other kinds of things to be able to solve sort of real-world PDEs in that kind of way. Okay, let me turn to a different thing. Let's talk about programming. We've talked about sort of industrial strength applied mathematics. Let's talk about industrial strength programming. So one question is, how do you make code more robust? So a big thing in this version is a framework we call the confirm enclose framework. So the issue is you've got a piece of code, and somewhere in that code, something goes wrong. And what do you do about it? How do you propagate that error? Well, this is a kind of a symbolic way to propagate the error. So we say f of x, confirm of y, z. Okay, y, there's nothing wrong with y. So the enclose that catches that confirm just says, oh, there's nothing wrong with that. It's just f of x, y, z. But let's say that y was actually $failed. Now that confirm will fail, and it will propagate that confirmation failure out to the enclosing enclose, and that will now return a failure object. So let's say you're writing a function called add2. You could say, let's write an enclose inside my add2 function. And now if I say, add2 of 4, great, no problem, it's going to give 6. If I say add2 of missing, that's one of the things that confirm by default triggers on, it'll just give a failure object. So this is a way of sort of, if something goes wrong, controlling the sort of the spread of errors, so to speak. And as soon as the confirm fails, as soon as it fails to confirm, it will immediately go out to the nearest enclosing enclose. So there's a whole family of these functions, So for example, another one is confirm by. And so this says, can you confirm that by this function number q that this is a number? Okay, great. Can you confirm that x is number q? No. So that's now a failure object. And similarly here, we can say, let's write something like this, which asks to confirm that the thing we gave first is a string. Okay, great. Let's do this. Oops, that's not a string, so make it a failure object. And now we can say, let's now look here at confirming this world thing. We now confirm the world, this world function. Now we can map it over that, and it's going to work just fine. Now let's say we do this. We map it over this, and now we've got an individual confirm there, and that confirm will eventually fail, and it will propagate to the outer enclose, and so the whole thing will become a failure. Okay, so this is an important thing for taking code that you write and making sure if something goes wrong, if it didn't end up being the thing you thought it was going to be, propagate that error outwards without having to write a lot of complicated code that checks for the error all the time, if this, if this, if this. There's a family of these functions. Confirm by confirms by a function, confirm match confirms that the thing that you get matches a pattern, confirm quiet, confirm that the thing was quiet and generate a message, confirm assert, just check that this particular assertion is true, and so on. The actual design of confirm enclose is quite interesting, kind of under the hood. It's a combination lexically, dynamically scoped thing, which is probably going to be a model for other things that we do going forward. Another thing that's a practical thing in this version is a thing called with cleanup, which is a way of ensuring that certain cleanup code gets run even when there's an abort, even when a confirm makes you jump out of something, this cleanup can still happen, and so on. For debugging, we're adding some things in version 12.2. If we just have this table, okay, great. We can say, let's put in here, let's say we want to know how long did these things take. So let's put in just EchoTiming here. And I can say, that, and now this is going to tell me how long each of those took. Or I could say, put in an EchoEvaluation here. There we go. And now it will show me what the input and output for the evaluation was and how long it took. So these are just convenient things to be able to insert in your code. Just like Echo, you can insert anywhere. It still returns the usual value, but it produces some sort of side effect showing you what's going on. Okay, on the subject of making code beautiful, one of the things when one often writes pure functions in Wolfram language, and I've, for quite a few years, often liked using escape fn escape to write a function like that. One thing we're adding, I'm afraid I don't think it's working yet in this version, is that you can just type vertical bar dash greater than, and you will get one of those function objects that just like if you type dash greater than, you'll get a nice rule symbol. There's just a convenient way to write function in Wolfram language, and a sort of elegant thing here. Okay, so another sort of programming convenience, a function called apply to. So let's say I have an image here. Now I could say, let's say I want to color negate that image. I can say apply to that image. So I say image at equals color negate. Now the image will be equal to the color negation of the image. Okay, there are also another number of other new functions like fold while, which is joining the nest while, take while family. Another thing that's coming, people may know that it's about to be the centenary of combinators. It's sort of the first actual concrete instance of a universal computation, first sort of announced in December of 1920. As kind of a part of the sort of celebration of the centenary of combinators, we're making sure that we can support combinators well in 12.2. Combinators, as in much early mathematical logic, involved writing down function compositions with left associative function composition. Normally, our function composition that we write with an @ sign is right associative. It goes like that. But left associative function application was a thing back in the day and is something that is important for dealing with combinators. So we're introducing this thing called application, which is a left associative function application as part of the combinator celebration. Okay, another completely different kind of thing. Let's talk about arrays and array gymnastics. So this is something where we're saying, let's reduce an array along a particular axis. And so this, for example, is reducing this array along its row axis. This is reducing the array along its column axis. And that's a very convenient thing to be able to do. We're saying essentially here, take a mean of the columns of this in this array. And this is a general function, array reduce. It has many, many capabilities for doing these kinds of things. Okay, so another thing that talking about code and so on, we're working on a big project in code assistant tools. I mean, think about kind of semantic checking. You know, we've got spell checking, we've got syntax coloring and so on. This is kind of semantic checking of code using machine learning and using rules and so on. I think it's going to be something that's very helpful in terms of quickly being able to write correct code. One small piece of that will be in 12.2 is something to do with code formatting. Let me show you that. So here we're going to take, let me open a new .wl file. So I say new package script.wl. So this is a new, it's going to be a new Wolfram Language code file. And now let me paste a big lump of code in here. Let's see if I've got this. Here we go. There's a big lump of code. I pasted in. Okay, there's a new button at the top here that says format cell. So I picked this cell, so I can now say format cell, and now it'll run an automatic code formatter on here with a certain set of choices about how to format this code. Now, if we pull up a palette, we've got here a code formatting palette. This code formatting palette has a variety of options for how to format the code. So there's a notion of what we call airiness, which is how airy is this code? How much does it make use of? How much does it spread out across lines? Let me see if I set this to full airiness, what's it going to do? Oh, there we go. So now it's made this code very, very spread out across lines. If I reduce the airiness level over here, we'll see something where the code is much more crunched together on different lines. And so one of the things we're doing is to provide these various kinds of settings to conveniently format code in different kinds of ways. So that's something coming first to the Wolfram Language code editor here. And we'll also be able to insert this kind of capability inside external IDEs. We've got a whole program of being able to take Wolfram Language syntax, coloring, and so on, and making it available inside all possible external IDEs. Okay, another thing that's coming, another big thing that's coming is a thing called form notebooks. Okay, so let's say you want people to enter some input. Maybe you want them to fill out some form. Okay, you can do that by just having something that you create with form function and so on. But let's say that you want something much more elaborate that has all kinds of notebook capabilities, but you want people to sort of be able to fill it out as a form. Well, then you can use this new kind of construct that we call a form notebook. And a form notebook is a notebook that you can treat as a form. So let me try to show you how this works. It's a little bit complicated to understand everything that's going on here. So we say insert here, and we can say insert a form element here. Let's say we insert radio buttons here. So this is now inserting a piece of code that represents radio buttons. So there are the radio buttons that we're going to represent here. Let me go ahead and insert something else here. Let me say, let's insert let's say a slider here. Okay, so that's the code version of it. That's the, and let's say we put something up at the top here. We say heading here, and we say, you know, enter the right value. Okay, so now we have an authoring form notebook. Now let's say, and we could also, let's just for fun, let's put an editable notebook area down here as well. Okay, so now let's say, let's generate from that. So what do we want to generate? We can generate various things, but let's just say, let's see, let's just say we want to, oh yeah, here, that's right. We want to create a form notebook, and then the form notebook is going to do something with that form. We'll just say create document. Okay, so this is now a built form notebook. Okay, so all those things, those controls that we put in, this is now the version. So let's imagine that you were generating a sort of a quiz for some education application. You would author it in the form authoring notebook. you would generate it as a form notebook, and then somebody might fill in values here. So let's say we fill in, something like this. Okay, there we got a result. Okay, now we say, given this form notebook, let's submit this form notebook. And that pull down that I was kind of ignoring before is telling us, what should you do when you submit that form notebook? Should you send the results to an API? Should you put it to a data bin? What should you do? Here, all I'm going to do is I'm going to just create another document from it. So I run that form notebook, and what I've generated here is an association, and that association is the set of results that I got from this. So it says key 1, that was the default name of this element of the form notebook, just has label B, and this one had a particular value for the slider and so on. And this is now the notebook piece and so on. So this is what I entered in that form. And this could have gone into a program to interpret, and I could have got something which just said, okay, I'll do some assessment of this and I'll tell me whether I got the right answer or whatever else. So this is a mechanism for authoring a form notebook. You deploy the form notebook. Anybody, all kinds of people can fill out this form notebook. The results of what they fill out can be sent back in a variety of ways for a program to then do computations on it. So one thing that's coming that is related to this, that you kind of see how this might fit in, is a function called assessment function. Assessment function is a thing that takes inputs. There's an assessment function object. It takes inputs and it tries to figure out, to assess those inputs, okay? So in this case, dog was a correct answer, cat was an incorrect answer. There's the assessment result object. Now this gets a lot more elaborate because the assessment function can be saying, move a locator around on a map and see whether you get inside a country border or not. Or put in this algebraic expression and see whether these kinds of transformations can take it to some other form or not. So it's a way of, it's kind of a little bit like interpreter, but it's a way of generally assessing inputs. And it's something that will be used a lot, I think, in connection with form notebooks, for example, for education applications. Okay, so we will also be building out a whole sort of courseware repository in which people can create things using form notebooks, using our course authoring tools, can make things that are basically just like the MOOC that was made from my elementary introduction to Wolfram Language, but all the tools will exist to just directly make something like this in a very convenient way. Well, something else, let's change topics a bit. Something that's always happening as we move forward with our computational language is kind of the growth of our knowledge base. And particularly given some new partners that we have, we've been kind of really driving that knowledge base in a whole variety of directions. So let's take a random example. Let's take food. We now support 500,000 kinds of foods. And there are about 20 or 30,000 in a typical grocery store. So for example, let's say we have a Kit Kat. I rather like those. There's a Kit Kat. And now we could say, let's generate the nutrition label from a Kit Kat based on our knowledge base. There's the result. So lots of different things. Here's one that isn't really my particular kind of thing. This is let's take 10 random weight training exercises. Okay, let's take one particular one. I barely know what this is, I'm sorry to say. Let's take, what do we know about a front raise weight training exercise? Okay, we could say, let's find out what are the muscles that are used in that. Now, of course, everything is now computable. So all these different muscles and so on, these are all computable things. So we could, for example, take them into anatomy data, anatomy plot 3D, and we could just plot where are those muscles, showing also a skeleton to attach them to here. It's got to load in all kinds of geometric data about anatomy here, but eventually we should get a result. By the way, one thing we've been doing a lot is optimizing the caching of things that have to be, the bucketing and caching of things that have to be loaded from the cloud for our knowledge base. So you'll see a lot of things, this one we haven't gotten to yet, but a lot of things were just much faster in terms of the way that large-scale pieces of our knowledge base can be loaded into, for example, a desktop Wolfram language. Okay, as it grinds away here, let me see. Well, there's lots of other pieces of the knowledge base. Why is this so slow? I don't know what's going on here. Who knows? I was going to show you all sorts of weird things. I had a note here about cultivars of tomatoes. Just one of the things that we're now into in kind of the structure of our knowledge base. By the way, another thing that happens in the knowledge base is really disappointing. Let me kill that. I don't know what. That is very weird. Okay. This is that's what I get for, as I say, showing you the very latest 12.2. Okay, that's something went horribly wrong there. Let's quit that and quit it. And let's just see whether, if I were to run this again, it might work better. I don't know. Okay, in any case, there's a lot of things now. What a silly thing to do. Why run it again? If it didn't work once, maybe it won't work again. So let's see. There are a lot of things that we might think of as data, but they're actually very computable data. So for example, here's an example. This is geometric scenes. Geometric scenes are another kind of thing in the knowledge base, but now there is a geometric scene, which is Euclid Book 5, Proposition 19. Here it is as a symbolically represented scene, which we can then say, let's get a random instance of that scene. So we're using kind of a knowledge base to get something which is now computable, and this seems to be a construction of some kind, and I'm sure we can compute things with it. Another thing we can do, another new thing is with the demonstrations project, we can actually, all of our 13,000 demonstrations, including many contributed by people who are probably here, are now available as computable objects in Wolfram Language. And so, for example, we could take one of those demonstrations and we could say, give us the manipulate that comes from that demonstration. And there it is directly there as a cell in our notebook, and we can do all kinds of computations with it. So that's another example of a way that the knowledge base has more computable kinds of things. And I might mention the whole notebook archive, which we're slowly building out, where one can store all these computational essays that contain these kinds of things. Okay, different topic. Let's talk more about kind of the outside world, now not in terms of computable data, but in terms of importing things. Big thing being added in version 12.2 is the ImportPDF. So this is now importing from a raw PDF file. This is now importing into computable data the first page of a fine paper here about which we can now do computations on. And in fact, for example, that picture I showed you earlier of the big word cloud of papers that cite Wolfram Language was got by just using importing of PDF from preprint servers. Okay, so another thing about the outside world, Wikidata data. Wikidata is unbelievably much messier than the kind of curated knowledge base that we have, but it's still convenient to be able to kind of poke at it and get things. This is now doing a geo lookup against Wikidata. Okay, in terms of things about the outside world, talking about kind of infrastructure of the outside world, this is a very practical thing. This is import of PEM files, permissions files. This is being able to import things like security certificates. That's a new kind of symbolic object in our system, is a security certificate of the kind that websites can issue and so on. And the importance of this is it kind of allows you to flow through kind of the infrastructure of the world, so to speak, carrying various kinds of authentications and permissions and so on. We introduced some system credentials, keychain related things in the previous version. Now we're introducing system credentials. Now we're introducing the capability to deal with security certificates. I mentioned our blockchain capabilities. We've been steadily adding blockchain capabilities. Here's an example. Blockchain we just added in the last couple of weeks, Bloxburg. This is the most recent block mined on the Bloxburg blockchain. So that's another kind of thing. By the way, as a practical matter, version 12.1 and 12.2 are compatible with the upcoming version 11.0 of the Mac operating system, otherwise known as Big Sur. Earlier versions are not compatible with that. Unfortunately, unlike Wolfram Language, which has remained compatible for 34 years, the same cannot be said of computer operating systems. We're not able to predict the future with respect to computer operating systems. So before Big Sur existed, we couldn't make things compatible with Big Sur. And that means only 12.1 and 12.2 are compatible with it. I mentioned, okay, so here's another practical thing. This is about RemoteEvaluate. So RemoteEvaluate allows one to remotely evaluate Wolfram Language code on a remote computer. So this is running on my desktop computer, and it's telling me that I have 68 gigabytes of memory available on that desktop computer. I was thinking I could run current image on my desktop computer, but that doesn't seem to work for some reason, probably a permissions issue. But in any case, you can imagine just running RemoteEvaluate, mapping it across a whole network of Raspberry Pis that are making various kinds of measurements and so on. This is a convenient way to do sort of remote computation. Okay, another long-awaited capability is being able to do remote computation, remote batch computation in the cloud. So for example, if you're going to use AWS, if you're going to use Amazon to run a bunch of big jobs, there is now a mechanism for using remote batch submit to submit jobs to your Amazon account. And so here we've got, this is probably some big messy thing about, comes Amazon credentials these are set up by another function, but now we can go ahead and say, let's submit this job now into the Amazon infrastructure to run as a batch job. And this is going to be running, what is this doing? This is a map job that's mapping across a bunch of different things. It's submitting that job, and we should now, once the job submission comes back, remember this is a batch job, so we're not in control of how long it takes. We can say once that batch submission goes through, we should be able to say, we're waiting for the Amazon system to accept our batch job. We should be able to say, show us a dynamic status visualization of the state of our batch job. And I don't know how long, it probably depends on how busy AWS is right now, how long it will take that batch job to submit. But we can go ahead and, well, it's taking an awfully long time. I may be timing out here. In any case, eventually it will submit the batch job to the Amazon infrastructure. We'll get back a task object. We'll be able to see how the job is running, and eventually we'll find out the job is finished. Okay, there we go. There's the remote batch object that represents our job. We can now say, show us the dynamic status visualization. This is saying there are 16 cores that we allocated here, 16 places where it's runnable. If we wait long enough, we will get evaluation results. Right now, if we ask for evaluation results, I suspect we'll get a big pile of missings. Okay, requesting child job metadata from provider. So this is now querying Amazon to ask the status of our job and ask whether the results have come back from these different parts of the job. Very boring, they're all missing, not available. If we wait for a few more minutes and run this again, we'll probably find that the job has been run and the results come back. Okay, but anyway, that's a practical capability for running large-scale computations, including machine learning and so on, with Wolfram Language. And there's a lot of moving parts that have to work to have this whole pipeline operate, and it does very nicely. We're supporting right now, Amazon will be supporting Azure in the future. We're also supporting Charity Engine, which is a kind of a public crowdsourced computing platform for doing large-scale computation. Okay, from talking that's a very practical kind of computation, let's also talk about another kind of computation. Let's talk about quantum computing. Our package for quantum computing is coming in this version. We've got, we can do all sorts of things. It's a little bit reminiscent of a neural net package because of the neural net subsystem, because it allows one to take these sort of blocks of computation and put them together. Now, I mean, and we can go ahead and do computations here, and we can say, let's actually run the thing. And okay, this is a quantum tensor product of quantum discrete states, et cetera, et cetera, et cetera. And we can actually run it, and we can compute some results here of actual probabilities for different outcomes and so on. Now, I mean, this is all well and good. This is a simulator of quantum computing. It's a whole different issue whether you can actually run this on a real quantum computer. One of the things that's really interesting about this is you can take our representation of quantum computing, and there's now even a function in the function repository that will simply compile this representation of quantum computing into multi-way systems. In other words, you can compile this representation of quantum computing into our model of physics. So in a sense, that's kind of, if you want to know if the model really makes sense, this is a kind of proof by compilation. You can take the representation of ordinary quantum mechanics and compile it into our model. And this is kind of the demonstration that that's possible. But it's also an interesting thing for just exploring quantum computing, although I think multi-way systems will actually, and our models actually provide a yet more powerful way to think about quantum computing and also show some of its limitations. Okay. Let's see. We talked a little bit about cloud deployment. There are all sorts of things that have become a bit more streamlined with cloud deployment. You know, the way it works on the sort of inside story of this, we have versions of Wolfram Language like version 12.1, version 12.2, and so on. The cloud is continually being updated. So we just pushed version 1.56.1 of the cloud, and there's a bunch of things coming in 1.57, which will be coming quite soon. And so the cloud is continually getting upgraded, even between different versions of Wolfram Language. It's also true that we have Paclets that are being field updated in Wolfram Language, as well as, of course, the knowledge base is being updated. These are all things that that can happen. Okay, so something that I think will be important. Oh, I was going to mention something else here about the compiler. The compiler is a big project. It's slowly coming along. Big thing that's happening that won't be quite in 12.2 is a lot of, but it will be in a Paclet update actually, is a lot of new tooling for using the compiler with dynamic libraries and being able to compile a piece of code and have it be able to be put in a function that's in the function repository, and have, when that function in the function repository is downloaded, you get the correct piece of compiled code for whatever platform your computer is using, and so on. Also, there are more data structures now and all kinds of other things. Okay, something important for developers is the Paclet system and Paclet tools. So in version 12.1, we kind of mainstreamed the whole Paclet system. Paclet system is what allows us to is what allows us to deploy a complex thing within a Wolfram Language environment. And by a complex thing, I mean not just functions, but also things like palettes and documentation and all sorts of other kinds of things that you can plug into the system. And by the way, something that's really coming is just an awful lot of other things you can plug in, whether it's your own version of a random number generator, your own format that you're importing, your own service connection, all kinds of different things. So that's something that's coming there. Now, one thing, when you build Paclets, okay, let me just start this up here. When you build Paclets, there's now in version 12.2, there's an elaborate system. And why is this not working? This should be coming up somewhere. Did it come up somewhere, but I'm not even seeing it? Oh, yes, it did. There it is, it's hidden. So this is the beginning of something which will get further developed. This is the beginning of being able to write documentation, just like the documentation that we write for the Wolfram Language. Write your own documentation. And now I can say, okay, let me just have a function name, test function, let's say here. And now this is, and now this will bring up, I hope, a function page. This is just like the function pages that we create for documenting a language. And you can fill in all these things. And this is kind of going to be deployed as a form notebook. And once you filled all these things in, you can then build it into documentation that can show up on the web or in product on the desktop for the Paclet that you've created. So this is a way to kind of create something which has the same kind of richness of documentation structure and so on as anything that we've been able to create directly in the main system. So that's a thing that you can then take all that documentation and put it in your Paclet and deploy your Paclet to the Paclet server. Coming soon will be a public Paclet repository, but you can also privately deploy Paclets to a Paclet server. Okay, so for example, another thing that's coming is the ability to make a new, just immediately to make a new, where is this? Oh yeah, there we go. Oh yes, new function page, new guide page. Okay, here we go. This is just, if you just want to make a disembodied guide page, a disembodied page that just is your favorite collection of functions that you want to use. This is a way to do that. And this provides you a variety of built-in services and will also allow you to deploy this so that it becomes a cloud page that you can then just have as something that you have as a favorite in your web browser or something like that, or something where you can just use this as a guide page to provide you convenient functions. So for example, we have one of these I showed earlier for our physics project. It's just a big list of the functions that we use in the physics project. And that's where I always go when I'm actually using one of those functions to go find the function that I can use. So a thing that we've really been developing over the last year is the function repository. So the function repository is a way of just adding functionality very conveniently to Wolfram Language. And the function repository it's roughly more than doubled the number of functions in it since last year. It now has 1,651 functions in it as of today, I think. These functions are all things that go through a curation process, a review process, but they're written by the community. And they're just all kinds of different functions here. And I don't know, let's pick a random example. I don't know, sky position chart. Here it is. And what's really important about this is I can just click here. I can go to my notebook. I can just go to my my notebook anywhere, and I can just say wherever my notebook was. Let's see, where was it? Let me pick the right one here. I go to my notebook here, and I just paste that in, and now it's a resource function. And oh, great! This is very sick in some way. Okay. You see, this is what I get again. This is a, you know what, this is probably some interaction with those Paclet tools that I just showed you. So let me quit this and start it again. And you see, this is always one of the interesting things with these keynotes. These are very real life kinds of things. Okay, so here we've got this resource function that I just copied from that page. And so what should happen if all is working correctly is that we should see, well, it's doing this, but we should just see that it loads in that function. Oh, wow. How weird. Very weird. Okay, well, let's try another one. Let's try something to do with, here's a COVID-19 epidemic data. Okay, let's try this. Let's try pasting that in here. Okay, so let's now just see whether that works. It says finding resource, and now it should if it's not horribly broken. Okay, there we go. So now it's just running that function, and what's convenient is that function. The function repository just had to give the definition of that function. It was leveraging everything we built in Wolfram Language to be able to know, oh, there's these entities which are countries, there's all this structure of associations and so on and so on and so on. There are all these things that we're able to take where it's where we're sort of leveraging the all the capabilities. What's this? Let's see. That wasn't what I needed. Let's look at what this actually is. Okay. Oh boy, this is a very complicated there's a very complicated set of things that one has to go through here to get this example. But by the way, this is using click to copy. It's very convenient to get examples from here. But we could pick a random entry from the function repository. I could even do that programmatically. And the whole point is that the function repository, what makes the function repository make sense is that you've got all the Wolfram language to build on. Typically, when people build libraries for low-level programming languages and so on, you'll have a library that's, for doing some particular kind of image processing. You look at the library, it's got 300 functions in it. And, 295 of those functions are support functions that deal with the processing of images in this way or that way. And only 5 of them are really the killer functions that are actually doing the interesting, unique thing. But you had to build all that support because you didn't have this kind of whole computational language to provide a representation of all these kinds of things computationally. In Wolfram language, we have that. And so when we build a function repository function, we can just add that one little piece of functionality for the one thing we want, building on top of that existing computational language. And I think that's a very powerful combination. And by the way, you can take those things written in some low-level language, let's say a Python program or something. You just take any one of those Python libraries and you can just wrap it as a function repository entry. And that's something that it's a non-trivial piece of software engineering that we can get that, they're different versions of Python. They're not compatible. They're weird library things that happen, weird dependency tracking and so on. I think we're slowly getting all of that sorted out so that you'll be able to just say, here's this thing. It happens to be implemented using this external Python library, but you can wrap it in a function repository entry, and you can just run it just like I ran any of these other things. And the fact that it calls this external code is not relevant. It's still running using all of the capabilities of our computational language. I should say, by the way, that I think as we build out the Paclet repository, Paclets are things where you can create a whole new world in a Paclet. You can change everything about the interface to your Wolfram language. You can change all these functions. But it's, you're kind of, when people use that Paclet, they're diving into this whole world. You can also have just a single function repository entry where people are just using this particular function in the usual world of the Wolfram language. I think there's sort of a combination that we're starting to use, which is there is a Paclet that contains a lot of complicated stuff, but it sticks its head out, so to speak, through a few particular functions in the function repository. And so really the way that people have to think about this Paclet, they don't have to think about the whole big structure. They just have to think, I want to use this particular function. Great, I can use it in this way. Okay, well, so, and by the way, when I should say that you can do things like put Paclets in GitHub. You can create GitHub repositories. It's a good thing to do. It's great for, it will be nice to see more GitHub repositories based on Wolfram language. It makes us look bad when people are not bothering to put things in GitHub because they just need to write a few lines of code, but it's still useful to put it there because it helps people to see what's possible with Wolfram language and so on. By the way, already in version 12.1, I think at the late stages of version 12.1, we made it a lot easier to enter data in the data repository, to get data to the point where it is computable enough that you can just read it directly into Wolfram language. That's a really good thing to do if you're trying to publish data that you're creating. By the way, the function repository is also a good place to publish things that results. Now that we have this whole ecosystem of citing functions, it's like publish your results as a function in the function repository. It then becomes a thing that can be used as part of the process of creating research papers and so on. I think that it's, in general, publishing notebooks to the cloud is something that's just a really great way to publish things, and particularly when it comes to kind of computational essays that mix sort of narrative text together with computational language. Well, I've gone on way too long. I haven't gone on as long as I did last time. We had more functions to talk about, but I have managed to get through them more quickly than I did last time. I think maybe I should, I've tried to give you some sketch of what's coming in 12.2. It's a longer story, what's coming in the longer term. There's lots more things coming, lots more things that we've been developing, things we've been developing for a decade that are slowly moving towards fruition. I think the thing that I should say to kind of try and close this off is, we've been working very hard. We've been working very hard for the last 34 years, actually, to develop this whole capability of this computational language that we have, I think that it's gotten a long way. It's kind of an interesting process that the further we get, the further we can see about where we could get to. And that means we've been seeing kind of this accelerating trend of the kinds of things that we can sort of make computational. And it's allowed us to kind of have this, we've been gradually sort of making more and more of the world computational. And I think we've gotten a really long way in doing that. Although from where we are now, I can see even more things to do that with. The challenge now is to have the world really be able to take advantage of what we've done and really take advantage of this kind of computational paradigm. As I say, many of you are sort of people who are bringing artifacts from the future into the present day and making use of these capabilities. It's kind of a neat thing to do. It's sort of a superpower that you can bring in to apply to different kinds of things. I think we sort of have a responsibility to try and deliver this message to a broader range of people in the world and a broader range of organizations. We're doing our best to try to make that happen in terms of making sort of our computational intelligence available in the most effective ways through the most effective channels with the most effective partners and so on. But it's something that there's just a huge amount to do there. It's something that is kind of an exciting thing because we're at this kind of watershed moment in intellectual history where this kind of computational paradigm that is kind of a great new thing. It's maybe the last such paradigm was perhaps the mathematical paradigm, which is maybe 400 years since it sort of became streamlined. We've now got such a paradigm. It's kind of a terrific time to be around and doing things. And I think we now have, as I say, something which perhaps in some ways is a kind of is a thing brought in from the future, but brought to today, and something that we can all make use of. And it's something where I would like to encourage people to do what we're trying to do, but we're just a small company really focused on trying to plant the seed of technological capability to really deliver what's needed to actually make this sort of computational paradigm to take root and to really make it to the point where sort of one can rely on computational intelligence everywhere and where people understand computational language as they today understand things like mathematical notation, and where people can use that computational language as a way to provide sort of a foundation for sort of computational X for all X. And I think there's just an awful lot of wonderful things that can happen as sort of all these things, all these X's become computational X's. And as we can bring sort of the clarity of thinking and that computational X brings to all these different fields. And by the way, also allows one to bring in a lot of other people who might not otherwise have been able to access those kinds of fields with this kind of computational way of thinking about things. It's just much broadens out the kind of people who can contribute to what's going on, because in a sense, you're sharing the burden with your computer. By expressing things computationally, you immediately have a collaborator, your computer, to do things. And that's something that we sort of increasingly see. I mean, I've seen that, for example, in our physics project. That's something, as well as great human collaborators, it's really critical to have that computational collaborator to really do things which I think otherwise would not have been possible and would not have happened for a very long time. All right, well, I should wrap up there. Thank you very much and welcome to the conference. I know there's lots of interesting talks that are going to happen, and lots of get-togethers, which I look forward to attending. I'll be doing a sort of Q&A session, I think it's tomorrow, about whatever people want to ask about. And I would say that the things I've talked about sort of the near-term future of 12.2, I think most of those things will be covered by particular talks, and people are welcome to ask about them, and look forward to interacting with people over the next few days. All right. Thanks very much.